relative abundance and thereby the efficiency of co-scattering in the early universe is directly connected to the mass splitting between dark matter and its mediator. This means we have a clear prediction for collider searches today. We observe a compressed spectrum of dark states because we need it for the efficiency of co-scattering. A second prediction that co-scattering makes is that if we compare it with perannihilation from freeze-out, we see that we can satisfy the relic abundance through exponentially smaller couplings than if we were working with a general freeze-out, with a perannihilation freeze-out. And the reason for that is that in co-scattering, our dark matter particle scatters off basically massless particle from the thermal bath that is not Boltzmann suppressed. So this process is much more efficient than perannihilation of two heavy dark matter candidates. And this smallness of the coupling to set the relic abundance tells us that we really expect long-lived mediators. So we expect this interaction to be feeble and thereby the mediator lifetimes to be long compared to the Hubble expansion in the early universe, but remarkably also to be long at the scales of colliders. So we expect to see displaced vertices at the LHC. So far about co-scattering freeze-out. Let me quickly explain to you what the predictions of freeze-in are for collider searches. So let's go a similar scheme as we just did for co-scattering and look at the main properties of freeze-in. So in freeze-in, the dark matter abundance is slowly populated or gradually populated until some time where the mediator that populates the relic abundance through decays is not abundant anymore because it has frozen out itself. So the crucial ingredients for freeze-in to work is that the mediator initially is in thermal equilibrium with the bath, whereas dark matter is not. So this already tells us a lot about the interaction between dark matter and its mediator, right? So we know that this interaction must be extremely tiny for dark matter never to reach thermal equilibrium. And moreover, we know that most of the dark matter production, so this process is most efficient at temperatures comparable with the mediator's mass. So with these two ingredients, we can again make predictions for what to expect at the LHC. The relic abundance, the observation of the current relic abundance together with these two ingredients for freeze-in tells us that we will encounter a split spectrum of states, and this is mostly because the freeze-in process is very efficient and we need a large separation of scales in order to fit the relic abundance within the current bounds that we basically have for producing a dark matter mediator at the LHC. So if we set that at the TeV scale, for example, we expect dark matter to be of the order of the kilo-electron volt or mega-electron volt scale. And the second prediction that we have is that since freeze-in only works out of thermal equilibrium, we will definitely see long-lived mediators because their decay, their overall decay is suppressed if the annihilation into dark matter particles is the dominant process. So now that we have these two predictions, right, we have basically two clear scenarios that we can test for at the LHC. So rather than searching for anything with long-lived particles, we now search for co-scattering or freeze-in dark matter. Of course, there would be other scenarios, but let's focus on these two and let's take them as examples to see what they really tell us and how they guide our searches for long-lived particles. So our guideline here will be mostly the relic abundance that connects the mass of the mediator to its lifetime and therefore spans some function, maybe not a straight line, but I think generically one can say that heavy mediators are expected to decay faster whereas light mediators often live longer. And this sets the stage for our LHC experiments to probe them, namely ATLAS and CMS will be the players to probe weak scale dark matter, whereas LHCb and PHASER, the long distance experiment that is just under construction, will probe light particles around the GeV scale. Very good. So let's dive into it and see a bit more concretely what to expect to see at the LHC. Here I give you two examples of how one can generically estimate the lifetimes of mediators given concrete scenarios of setting the relic abundance in the early universe. So in co-scattering, you see that if one does a rough estimate and takes natural values for weak scale dark sectors, we expect proper lifetimes of the order of the centimeter range, whereas in freeze-in, we can have lifetimes that reach up to a few meters. So comparing that with what we expect to probe at the LHC, we see that just by the way the detector is made, we can probe displacements of the order of 200 micrometers. So this is just the resolution. So basically when ATLAS and CMS are able to detect a displaced vertex up to about the range of a meter, which would be the outer shell of the calorimeters. So this means that indeed co-scattering and freeze-in are scenarios that predict lifetimes of mediators that are in the reach of the LHC. This is highly non-trivial, as I said before, but we of course go ahead and exploit it. So this wouldn't need to be that way. It's really a highly non-trivial connection between cosmology and colliders, and I think we definitely should not miss it. So what do we expect to see? So how do we now probe co-scattering and freeze-in and other dark matter scenarios with long-lived particles? This nice picture summarizes different signatures that ATLAS and CMS have searched for already or have thought of by using different model hypotheses. And of course, not all signatures are predicted by all scenarios. And the question is now, so how does dark matter fit in here? What predictions does dark matter make? What do we expect to see? In order to explain that to you, I would like to be a little bit more concrete and focus on dark sectors that have weakly interacting mediators. So weak really meaning the weak force. If you're familiar with supersymmetry, you will directly recognize them as a Higgsino-Bino-like electroweak kinos or as a Wino-Bino-like electroweak sector in supersymmetry, provided that the third type of electroweak kinos is decoupled. So you can also think of that as some Higgs portal interaction of two fermionic states that have different weak gauge quantum numbers and that can mix through electroweak symmetry breaking because they generically couple to the Higgs that induces a mixing. And you can see that we can have different ways for the mediators now to decay. So typical signatures one would expect would be a long-lived mediator decaying into the invisible, into missing energy, and then through some heavy gauge boson into leptons or jets. And generically, if these portal interactions are small, we would expect the mediators to be long-lived. So these simple scenarios have all the ingredients that we basically need in order to construct models that feature alternative ways to WIMP dark matter. So what do we actually expect here? We can see very concretely that within these models, co-annihilation, co-scattering, and freeze-in can all be realized with this minimal model content. And here you can see two examples that actually I have condensed basically to describe 4 of the main signatures that are predicted for the LHC, namely disappearing tracks. So this would be a charged mediator that traverses a certain length before decaying. We could see displaced B-jet pairs, B-jet vertices from Higgs decay. So that would be the dominant mode if the decay is Higgs mediated. We could expect displaced soft leptons and missing energy, or we could expect this, or we could see displaced leptons or jet vertices if the interaction is mediated by a W or Z boson. So there's a variety of signatures predicted, and the variety basically comes from the fact that the dark sector is weakly interacting. So that could be different. For example, for a strongly interacting dark sector, we would expect maybe emerging jets or dark showers. So there are different types of dark matter scenarios that can predict different signatures. But what is common to them is that if their radical abundance is set by non-WIMP mechanisms like co-scattering and freeze-in, they would always produce signatures of mediators with similar lifetimes. So this means that this model dependence that we of course need to use to have a concrete search is not as big, but these predictions from the early universe are quite generic because the dependence on the coupling and the mass spectrum is so strongly set by the temperature effects. So now the question is, of course, what if we look at these signatures, what do we learn? What do we learn about the production process of dark matter? So you can see here one example of, this is for Wino-Bino type dark matter with no supersymmetric assumption. And you can see different signatures that one would expect at the LHC as a function of the mediator mass and the portal coupling that induces the interaction of dark matter with the visible sector. And the take home from here is basically that depending on the strength of interactions, we expect very different signatures to happen depending on what decay channel is most prominent. And we can also see that depending on what signature is predominant, we can have different processes that play an important role in the early universe and set the radical abundance. So we are after co-scattering and freeze-in here, and you can see that these happen predominantly for very small couplings as we predicted. And we can already say, okay, disappearing charged tracks and displaced soft leptons seem to be good observables to probe these FIMP dark matter regimes. So let me give you just a little bit more detail about how to concretely search for co-scattering with soft displaced leptons. So the softness of the leptons, or could also be jets, is due to the compressed dark sector that we needed for efficient co-scattering in the early universe. And this requires that we have to be able to detect soft displaced leptons. There have been previous displaced lepton searches by Atlas and CMS, but setting quite a high threshold for the transverse momentum of the leptons. In this analysis, this momentum threshold has been lowered at the expense of accepting a large background from B-hadron decays that also have finite lifetimes. So from a multivariate analysis of soft displaced lepton signals at the LHC, we were able to predict that the LHC during run 2 or after during run 3 should be able to probe lifetimes of the mediators that correspond to the range where we expect co-scattering. Remember, this was in the centimeter range, and that basically everything that is above this dashed line here could be probed with current or future LHC data. So this is a proof of principle, basically, that yes, we can search for soft displaced leptons, but the main challenge here is a big background from hadronic B-meson decays, leptonic B-hadron decays. So this means that at some point we will have to deal with really high event rates, and this requires the design of dedicated triggers in order to allow us to be able to deal with an enhanced event rate, or in order to create new features or to trigger for new features in our signature in order to reduce the event rate. So this will be one of the main challenges generically in extending the long-lived particle searches to less conventional searches, like going basically beyond detecting displaced vertices, which are often considered as one of the easiest signature. So going beyond will most likely require refinements in triggering or in exploring new techniques, could be at the hardware or software level. So now that we have learned about the details of co-scattering at the LHC, let's talk a bit about freeze-in. So what to expect from freeze-in for colliders. I just quickly wanted to summarize the stage, so what we expect at the LHC. Remember that the efficiency of freeze-in required, together with the relic abundance, a large separation of scales in the dark sector, so a very heavy mediator decaying into a very light dark candidate, and then producing at best a vertex of displaced charged particles that we could search for. And also remember that the lifetime prediction was very long because dark matter was initially out of thermal equilibrium. So now we have a lower bound on the dark sector as well. And this is mostly because freeze-in should happen in the early universe well before structure formation, and it should be cold. So it should not be warm or hot dark matter in order not to dilute, not to wash out the structures that will later on form. Structure formation actually sets quite a strict lower bound on the dark matter mass, and this gives us a lower bound on the mass of the mediator particle. So if we know that at the LHC we have an upper limit on that, so the range of freeze-in scenarios that we can probe with mediator decays is actually limited. And this you can see here. So again, we see the reach of the LHC as a function of the mediator mass and the mediator lifetime. And you can see that structure formation basically excludes this region of short lifetimes. And if you look at the ways the relic abundance can be obtained, we see that unless dark matter is very light, the lifetimes of our mediators will be too long to be seen for the LHC. So that could be an opportunity either for a future high energy collider that is able to produce heavier mediators, or to go to like external far distance detectors that are able to probe longer lifetimes. That would be, for example, Methuselah, as you can see here. So this example shows us that there's ways to improve and to enlarge the potential reach of the LHC for freeze-in scenarios. Another option is not to consider freeze-in during the radiation era, but to assume a different cosmology, or what it means to assume. So if nature has chosen early matter dominance, for example, an early period of matter domination, the freeze-in process is much less efficient, and we require a larger interaction rate, a larger decay rate of the mediator into the dark matter to populate it efficiently again. And this means, in retrospective or in reverse, that we expect shorter mediator lifetimes. And you can see here that if we lower the reheating temperature, so basically the temperature at which we switch from a matter-dominated to a radiation-dominated universe, so if this temperature gets lower and lower, the lifetime for a fixed mass gets shorter and shorter, and scenarios come within the reach of the main LHC. So I think the LHC is the perfect machine to probe freeze-in during matter domination, whereas freeze-in during radiation domination most likely requires a high-energy collider or a far-distance experiment. So here I would like to summarize the opportunities for ATLAS and CMS to search for non-WIMP dark matter scenarios. We've basically already heard all this, right? So let me be brief here and just mention that self-interactions, which I have not talked about today, can also play a big role in setting the Rayleigh abundance. So self-interactions can create number-changing processes that affect the freeze-out in the early universe. They also have cosmological implications, and if these sectors are strongly interacting, so if there's some confining force going on in the dark sector, we expect to see something like dark showers at the LHC. And currently within the long-lived particle working group at CERN, there's a big effort to tackle these signatures with dark showers as well. In the last few minutes, I would like to take it to the GeV scale. So far we have mostly talked about weak scale dark matter. Now let's look at what happens at much lower scales, which would be the domain of LHCb and phaser. So the first point I'd like to make is that the production mechanisms of dark matter in the early universe, most of them are not tied to a mass scale. And to illustrate that, I just want to allude to co-scattering and freeze-in again. So for co-scattering, what sets the Rayleigh abundance where the relative number density is combined with a small interaction, and that doesn't involve any mass scale, right? So all that matters is the relative masses of the dark sector particles. This means that we can move it to any scale basically, but of course within certain limits, because it's not only the Rayleigh abundance that counts for a viable cosmology. Similarly for freeze-in, we can have processes that are different from the decay of heavy particles.
Okay. All right.
For example,
I'm tuning into another meeting simultaneously.
So for example, rather than having decays of heavy particles, there could be scattering processes happening. And in that case, the Rayleigh abundance would be set slightly different than we discussed before, but freeze-in would still happen. So this means that not only decays of heavy particles, as I showed you before, are relevant in setting the Rayleigh abundance, but other processes can as well be effective in the early universe and should be explored. And this means that GeV scale or experiments sensitive to GeV scale physics have a good sensitivity to alternative production mechanisms of dark matter. To give you an example, here I show you a scenario, a concrete scenario of co-scattering, where the interaction with the standard model bath happens through a dark photon. This must be, of course, a light, like light mediators should better be electrically neutral. So this means that we have to build in order to find this co-scattering phase, but it would always appear as we lower the interaction strength with the thermal bath. And from this busy plot, you can see that dark matter around the GeV scale, co-scattering dark matter around the GeV scale could be probed by all kinds of signatures. There are cosmological signatures. It's a good opportunity for direct detection with electron scattering as well, as you can see up here. And there's an opportunity for flavor experiments to probe co-scattering. So now the question is, where is LHCb in that game? And I would like to take the opportunity to encourage LHCb to really exploit the full potential of long-lived particle searches. There have been searches for long-lived particles, but we think, and there's also a lot of effort going on in order to really broaden the scope and explore LHCb's excellent capacities in vertex reconstruction and mass resolution, and to think out of the box of what LHCb can do in order to probe GeV scale long-lived particles that could be signatures of dark matter. So here I just show you as an example LHCb's most recent search for dimuons. So these are displaced muon pairs, and it's a fully model independent search that can be applied to different scenarios in order, for example, to constrain or to probe dark matter interactions with muons, with leptons. With this, I come to the end of my presentation. As a take-home message, I think you can remember that I have shown you that long-lived particle searches are indeed sensitive to dark matter, can be sensitive to dark matter scenarios, and also that by imagining different ways of early universe dynamics, we make concrete predictions for long-lived particle signatures at the LHC that guide our searches and that also push us to the limits of what current searches can do. So in order to really exploit the full potential, I think triggers are a really important topic. Timing information has the potential to also tackle difficult long-lived particle signatures. And I think one really has to explore the complementarity of the different LHC experiments, but also go beyond that and connect LHC observations with observations at flavor fixed target and neutrino experiments. And then importantly also to connect back to cosmological observations and try and explore this mutual feed of collider searches and what we have learned from colliders into cosmology aspects and astrophysics, for example, structure formation at small scales, and vice versa, to use recent results there in order to learn about where to search at colliders. So with that, thanks a lot for your attention, and we can have a quick break for questions.
Thank you very much, Susanne. So to everybody, Susanne will stay around, of course, in this session and have immediate questions now and maybe some more later. But before we continue, I want to introduce to you this session's discussion chair, which is Kingman Chung. Welcome, Kingman, from the National Tsinghua University in Taiwan. He has the chair of discussion and he will lead you through the rest of this session. Kingman, the floor is yours.
First, thank you, Suzanne, for excellent talk. I really learned something from cold scattering and freezing dark matter. So, so we invite questions from the audience, participants, panelists.
There is one raised hand. I gave him the right to speak.
Yeah, all right. Thank you, Susanne, for the very nice and inspiring talk. So I have a question on page 22 where you discuss this freezing scenario. And I was just curious, what are the possible production modes that we are talking about here? So you're producing it's just pair production of those M2s, or is there something else being produced in the event?
So here in this search, the focus was mostly on displaced vertices, right? So this was a Higgs-Sinobino-like scenario, and it was searching for one displaced vertex and missing energy. So these were the two characteristics of the signature. There are other opportunities, right? So disappearing tracks can be an option if the mediator is charged, but these are of course quite generic. And then depending on the open decay modes, one could also be interested in heavy stable charged particles. So if the lifetimes are really very long, right? This is like our hadrons, these searches would become relevant. One could experiment with displaced jets. So leptons are not really a prediction of that scenarios. That could just as well be displaced jets. Flavor tagging is also an interesting option to learn more about the specific decay channel, for example, if it's Higgs mediated or if it's gauge boson mediated. All these are options, and what these analyses here have done is to recast existing searches. So this is not really optimized for freeze-in searches, but these are reinterpretations of what has been looked for different purposes.
Yeah, thank you. My question is actually even a bit more basic. So I see this Feynman diagram on the top, right? And it just shows one of the M2 particles decaying. And I was just wondering what could potential production mechanisms look like? Would it be just pair production of a pair of M2s, or would it be a pair of M2s with yet something else, which could perhaps serve as a trigger? This is where the question is coming from.
Yes, so for this, I think it's useful to go back here, if you can see my slide 17. So this would, you can see the signature that I showed you earlier here. On the other side, it depends a little bit on the branching ratios or on the preferred decay modes. But usually it's electroweak production for weakly interacting dark sectors. So this is really very similar to what happens in SUSY for Higgsino and Wino searches. And potentially one can combine signatures from both sides. So there can be an option of having one side decaying promptly and the other side being displaced, both sides being displaced. And I think you have some freedom to design a signature that is experimentally clear and still probes a certain region of parameter space. It's just that, like, depending on how you design the signature, you will probably limit the generality in terms of interpretation. So if you stay generic and just search for displaced vertex and the missing energy that you always expect from dark matter in the final state, you would be able to apply that search to a larger class of models and also to cover more parameter space within one given model.
Okay, thank you.
Suzanne, I have the related questions for this one. For the freezing scenario, there will be a huge large mass splitting between XD and XS. But in the SUSY framework, in SUSY framework, such large mass splitting is not natural. Do you have any other more natural model that have such large mass splitting between M2 and M dark matter?
It's a very good question. I think there has been little model building as far as I'm aware. And of course, there are always counterexamples. I think such a scenario might arise if we work with a split. So if we work basically with a scenario where the mass of one particle is protected by a symmetry that is slightly broken and the rest of the dark sector would live at a different scale. But I think it would definitely be a non-trivial, or how to say, a non-minimal scenario, right? So if we see freeze-in at the LHC, of course, we cannot immediately conclude from a long-lived particle search that we have seen freeze-in. But if we do, right, if we get further insight into the scenario, then I think we could be pretty sure that we have actually discovered two scales, because radiation era freeze-in only works with a large scale separation. So that, I think, would be an indirect conclusion we could learn. But in terms of model building, the floor is yours.
Okay, thank you. Yeah, there's another hand will raise up.
Hello, Suzanne. Thank you so much. This is Ashutosh Kotwal from Duke. Wonderful talk. In fact, your slide 22 right here is the best for my question. So if Methuselah is looking for neutral particles which are sufficiently long-lived, so if there was equivalent charged particles which are sufficiently long-lived, then is it fair to say that for the appropriate C tau, they would look like muons? Assuming this is all weakly interacting, then it just looks like a heavy muon produced in ATLAS or CMS, So at the appropriate C tau of a few meters with a beta gamma factor boosting and all that, the muon triggers in the LHC experiments, Atlas and CMS specifically, should be able to produce detectable signatures. So I wonder why in this paper, for example, there isn't some kind of bound showing the sensitivity to the heavy muon-like charged particle, which can be triggered and observed.
Thank you very much. You mentioned a really important point that I somehow skipped under the carpet, even though I wanted to mention. I think it's really a good opportunity for long-lived particle searches in the muon chambers of Atlas and CMS. So yes, they would have sensitivity, and we don't know how much, but it's true that like it would be a heavy particle, so it would be a TV scale muon, but there would definitely be interactions with the muon chambers, and these should be exploited in order to probe for freeze-in. So this means that some of the Methuselah area I would expect to be probed by the muon chamber, but as far as I'm aware, this has not been explored yet. So there are ideas how to use the muon chambers, but there are no concrete analysis that one could recast and interpret them in terms of dark matter scenarios.
Very good. In fact, that's a very useful message for the experimentalists in the audience to carry back to our experiments.
Exactly. So to turn it around, it also means that, yes, put more effort into the muon chambers because they can search for longer lifetimes than, I mean, this is, I think, obvious just because the distance from the interaction point is larger, but they can also bridge the gap between the lifetimes that main LHC can cover and far distance detectors can cover, right? So this gap is well known, and this could be closed or partially closed using the muon chambers.
Very good. Just a very quick follow-up question. When you mentioned TV scale, why does it have to be so heavy? Why couldn't it be 1 GeV, 2 GeV? Does it have to be hundreds of GeV?
So the point is that structure formation sets a lower bound on the dark matter mass, and combined with the observed relic abundance, this gives us a lower bound on the mass splitting in the dark sector. So this means that if I want to satisfy the bounds from structure formation that are really rigorous, so this cannot be circumvented, so dark matter cannot be lighter. This means that I get a lower bound on the mass of the heavy mediator. And this means also that it's really difficult to see light mediators and still have a viable scenario of freeze-in. Right? So to obtain the correct relic abundance, you see that here in this green and darker lines, dark matter has to be very light if it comes from the decay of a heavy particle. Otherwise, you would need a smaller interaction rate in order not to overproduce dark matter from freeze-in, and you would end up with longer lifetimes. So if you want to probe like lighter mediators, you probably would find yourself with a modified cosmology, like, for example, early matter domination.
Okay, guys.
Thank you so much.
Yeah, this is a very interesting topic, and let's hold all the interesting questions in the discussion section. And shall we move on to the next talk by Martin? Oliver?
Yes, let's move on to Martin Bauer's talk. Martin is from the Institute of Particle Physics Phenomenology in Durham, and he will have the second talk on LHC hidden phenomenology or models. Martin, the stage is yours.
Thank you very much, and thank you very much for the invitation to talk here. So I was asked not only to talk about my own interest in feebly interacting particles, but also about the activities of the FIPS working group. Let me just try to share my screen. So if you don't say something, I assume that you all can see the screen now.
We can see it.
Screen as well. So that's what I'm going to do. There is a report out from last week. Here's the archive number, and what I'm going to show is heavily based on this. I will also give some personal highlights from this report, and for both theoretical and experimental questions that are still open in regard to feebly interacting particles. So what are feebly interacting particles? Well, they are loosely defined as new particles beyond the standard model that have interactions with standard model particles, which are strongly suppressed. And the origin of this suppression can really be anything. There could be an almost unbroken symmetry responsible for this. There could be a large hierarchy of scales, or there could be nothing in particular that is that results in such a situation. Now, it doesn't mean that the particle is necessarily light. It doesn't even mean that there is necessarily a new particle. So the Higgs, for all intents and purposes, is a feebly interacting particle for most of the standard model, in particular the first generation, of which we have no evidence yet that there are couplings between the Higgs and electrons or up and down time quarks. That is certainly something we should be looking for and find new ways of constraining it. In this very simple sketch, I show coupling strength versus mass. And it is, of course, easy to see light particles that are strongly interacting. The energy frontier would be strongly interacting particles that are heavy. And FIPS can be anything that is weakly interacting, but I'm going to focus on light particles for the purpose of this talk. We will organize FIPS into the way they interact with the standard model, and that depends on their quantum numbers. So I'm going to give a short review of the Higgs portal, the neutrino portal, the vector portal, and the axion portal, and what has been done in the FIPS report on these topics. Whether these portals are there is, of course, an open question. You could always ask this question, should there be a new interaction? But I would rather turn it around. I would say it doesn't really matter how sophisticated your UV model is, how nice your string theory is, and how cool your gut. If you end up with a particle with these quantum numbers, then you really should have a good reason why these portals are not generated by your theory at some level. So it makes absolute sense to look for them. I'm going to go through them in this order. Let's start with the Higgs portal. Now, if you assume you have a new real scalar field or a complex scalar field that obtains a vacuum expectation value, then you get a coupling to the Higgs boson of this kind, because H dagger H is a total singlet. And this gives rise to two possible interactions. One is a mixing with the Higgs boson, with this mixing angle theta that is set by these parameters in the Lagrangian. And the second is a direct coupling between the Higgs and two of these new scalars. These new scalars could in general be anything. They could come from any kind of UV completion. They could in particular be in the inflaton or dark matter, of which I will talk a little bit about. Susanne has covered most of feebly interacting dark matter in her talk. Now, how would you probe this experimentally? Well, the most obvious thing to do is to look for Higgs decays. Right? The Higgs portal induces a Higgs coupling. So this would show up in Higgs to invisible, which is by now constrained to about 10% of the total Higgs width. Or it could be giving you a signal when these scalars decay further. And if all the interaction are induced by the Higgs, then you can actually constrain this mixing angle in these models. So what I show here is from Atlas and CMS some constraints on these different decay channels. So there's a bunch of them. It could be 4 photons, could be 2 photons, 2 jets. You can go down to about 10 to minus 2 times the branching branching ratio here in these limits. Now, if you have lighter scalars, you can do better, because if you're below the Higgs threshold, mesons will decay resonantly into this new particle. What you can do now, and Susanne has mentioned this before, is you can look for resonance searches in these meson decays. So, for example, LHCb has done this. LHCb has searched for these new particles in the decay of B mesons into kaons and new states that then either decay promptly or travel a bit before they decay into pairs of muons. And you can see from the left-hand plot here that shows lifetime versus the mass of the particle, and there's a color coding that encodes the sensitivity of LHCb, that they actually get more sensitive if the particle is longer lived, which makes sense, right? If it's longer lived, then you can suppress your background better. You have a displaced vertex. So on the right-hand side, you see these results again. The light green corresponds to constraints in the mixing angle from prompt decays, and the darker green correspond to constraints from displaced decays. Now, you can go further, and there's a bunch of proposals for new experiments searching for long-lived particles. You all know Methuselah. There's Phaser, which is pretty much under construction along the beamline. There's Codex B for LHCb. And there's the proposal for Anubis, which would instrument the Atlas shaft, also orthogonal to the beam. All of them have the potential to do better than LHCb in that particular signature because they can look at vertices that are further displaced from the interaction point. So what I show you here is the first summary plot for the Higgs portal. You can see the constraint from the Higgs to invisible constraint on the right-hand side in blue here, and what the high Lumi LHCb would be able to do. The LHCb constraint that I discussed is shown in gray here, and run 3 will improve that. And if you want to go below for these masses, you see all these displaced vertex experiments proposals showing up. Now, what if the scalar is even much lighter than that? So if the mass becomes comparable to macroscopic scales, it induces a fifth force. And in that case, the strongest bounds come from a violation of the equivalence principle at different scales. So I show here a summary plot of a recent paper with Patrick Foldenauer and Peter Reinitz and Tilman Blaine, where we show the complementarity of these searches. You see Higgs to invisible here, and you see the different constraints from this equivalence principle violation on the left-hand side. That is clearly the case if you mix with the Higgs. It's actually also the case if you have two scalar exchange, then you have a loop that gives rise to a new force. And I've put some references here where you can read up on this. The plots then, the constraints then look a bit different. Now, these give you the strongest constraints in the case that this is just a generic scalar. If it is dark matter, you can do better than that. Why would it be dark matter at these very low scales? Well, there's a very good reason, and that is the fuzzy dark matter paradigm. If you go to extremely light scales, what happens is that the de Broglie wavelength of your dark matter particle becomes so large that it basically has the size of the galaxy. And why would that be interesting? Well, at that point, you end up with a theory where smaller structures than galaxies, like dwarf galaxies, for example, are harder to get in structure formation because the de Broglie wavelength can't really fit this galaxy. So this ultralight scalar dark matter leads generally to a better fit to the small scale spectrum, and you can address problems like the missing satellite problem, the core cast problems with this type of dark matter. However, the mass is pretty much set. So this 10 to minus 22 electron volts, this super tiny mass, is a consequence of the fact that you want the pressure from the uncertainty principle versus the gravitational pressure to cancel out exactly. So that's a very, very small parameter space where you can look for this type of dark matter, which changes if you have self-interactions. I'm advertising this because this is an argument for why this would be scalar dark matter actually. There's two types of possible self-interactions that you generically have at these scales. They don't need to be large self-interactions, even if they're very small that have an effect. If you have attractive self-interactions, you're helping the gravitational side of this equation, and that actually leads to lower masses, and worse, they induce instabilities. You get boson stars and clumps, and you don't really get the galaxies the way you want them to be. If you have repulsive self-interactions for this type of dark matter, you open up a range of scales, right? Repulsion helps the quantum pressure, and there could be heavier dark matter inside, because in order to balance this out and still stay the size of the galaxy, the gravity vector here can be larger. And now you would immediately think, if you want to go to these low scales, what you want to have is an axion, because you would want to have a way to protect that mass scale. You would want to have an explanation for why this would be so damn light. But the axion is actually a really bad candidate for this particular kind of dark matter, even though many people are working on it, because an axion always induces attractive interactions. You can trace that back to the fact that axions are Goldstone bosons from compact groups that give you a single cosine or sine potential, and that results in an attractive interaction. For a scalar, there is no reason the lambda term should be anything, like there is no reason the mass term should be any particular value, so they are actually good candidates for this. So how do you probe this type of dark matter? Well, the right density for this type of dark matter is really set by the misalignment mechanism, and that leads to oscillating background fields, right? So the light scalar oscillates in the potential, and its couplings through mixing with the Higgs, for example, to fermions and photons lead to variation that are time dependent in the fine structure constant and in masses. And you can see these things with experiments like laser interferometers, like gravitational wave searches. You can see them with optical clocks, like transitions in spectroscopy are hypersensitive and can constrain this to extremely low values of this suppression scale up here. much better than these equivalence principle searches. And you can do this in a new generation of experiments that works with atom interferometry. So MAGIS here is one of these experiments where you have a tower and you have atom wave functions that interfere, and you let them free fall and measure basically the radiation over the space they go through before they are combined again. So the parameter space for these light masses is shown here. All this green region is what we already know from the equivalence principle. The previous plot fits in the upper right corner here, and don't show you this. And you can see that MAGIS and ION, which is the European version of this future kind of experiment, will start to cut into the parameter space beyond what we already know from the equivalence principle. So this is really a new way and completely complementary way to probe the Higgs portal. Now let's move on to the lepton portal. The lepton portal is described by this Lagrangian, if you will. It says that if you add now a singlet fermion to the standard model, then you get an interaction that looks like this, because the L bar phi combination of the standard model is a gauge singlet again. For such a new fermion, you can also write a Mariana mass term that would then correspond to the CSO1 model. And this Mariana mass can be large, but it doesn't need to be large. And if it is not, the new fermions, these sterile neutrinos, could be in the reach of the LHC, for example. Now, the active neutrino masses and the mixing with the sterile neutrinos are related quantities. So you can see from here, if you want to solve this seesaw mechanism for the mass of the active neutrinos, then you can write this as the mixing angle acting on this large M mass matrix. And there's many reasons to assume that such a mechanism is there. In fact, some version of this is there for sure, because we know neutrinos are massive. But leptogenesis and dark matter are other good reasons to assume that we might discover something along these lines. Now, how do you see that the LHC? Similar to the Higgs portal, you now couple to the standard model gauge sector through this Yukawa coupling. You mix with a neutrino. So one way to discover this is through resonant production of W's that then can decay, for example, into 3 leptons, right? And that has been searched. So the signature is shown on the right here, the Feynman diagram on the left. Again, this can lead to prompt and displaced decays depending on the lifetime of this new neutrino. And the limits look like this. There's equivalent searches from Atlas as well. I just picked one, and they have done the search for electron sterile neutrino mixing and muon sterile neutrino mixing. They look pretty much the same. They can constrain these mixing angles up to the order of 10 to the minus 5. And you can see the structure emerges from the fact that you have on-shell W's until you go over the threshold in the sterile neutrino mass. For low masses, you can do better again. So as soon as you can have mesons resonantly decay to these particles, you can typically increase your sensitivity. That's also a general message. These flavor observers are very sensitive. And you see this on the left-hand side for compilation of constraints, and you see this on the right-hand side. And I've included this plot in particular because there's the NS62 result, which constrains these angles up to the order of 10 to the minus 9, which is really impressive, but only works if your neutrino is light enough for the kaon to decay into that state. So again, there's complementarity between collider searches that can constrain heavy masses and searches from these non-collider experiments. Here we see the parameter space for mixing with the electron for such a sterile neutrino. And you can see I've circled here the constraint from NS62. And for comparison, what Atlas and CMS can do, these are the contours up here. And they're catching up already with our best limits from lab. So the Z boson could, of course, also decay into neutrino and sterile neutrino. And Delphi has produced pretty strong limits for this mass range. But what we already have from CMS and Atlas catches up to them. And it's expected that the high Lumi LHC, we get new limits here that overcome them by quite a bit. Now, you also see all these dashed lines over here. And these correspond again to a number of displaced vertex far detectors that potentially can cut into this parameter space because they can see very far displaced vertices, well beyond what NS62 can do or other experiments that exist. Now I'm showing you the same figure for mixing with a muon. There's not much to say here. It looks similar. Part of the work of this FIPS group was to combine these different limits from dark matter colliders and beyond collider experiments to show what they can do and how they have the complementary reach. There exists therefore also a plot where you have the mixing with a tau, which looks a bit more empty, which emphasizes in particular the need for such a far detector, which can really say a lot for these particular final states. And LHC should certainly, the LHC collaboration should certainly search for these leptons, for these stereoneutrinos in the tau channels as well, right? It should be expected that they can be competitive here too, if they understand their taus well enough. Now, all these plots have been done for dominant mixing. So we assume full mixing with a tau, muon, or electron. And the final point I want to make here is that this isn't necessarily a good assumption. So it's difficult to work out general predictions of these models if you have more than one stereoneutrino. But what we know is that if you have these mechanisms that give you the active neutrino masses, that constrains also the mixing with the stereoneutrino by the PMNS matrix. The U here is the PMNS matrix that diagonalizes the stereoneutrino masses. So mixing angles to the stereoneutrino are constrained by active neutrino parameters. And these groups have worked out the constraints for a model with two heavy stereoneutrinos. And you can see that for normal and inverted hierarchy, these extreme scenarios where you have coupling to purely one, mixing with purely one standard model neutrino are actually not allowed. So one recommendation of this group is that in the future, we should also consider points that are actually allowed by neutrino mixing as benchmarks for further searches in these channels. Let's move on to the vector portal then. The vector portal is a similar story. If you introduce a new vector, any U1 gauge boson, there is a mixing term with a standard model hypercharge boson. And that mixing term can be written down in the first place. So there's no reason why you wouldn't have this operator unless you have a UV structure where you somehow embed this U1. But even then it could be generated and you could get it from loops of heavy particles. Whenever you do that, that mixing term, which induces a mixing between the hypercharge and this new gauge boson X, leads to a coupling of this new gauge boson with the electromagnetic current as part of the, because the photon is part of the hypercharged gauge boson. Now, the vector portal is particularly interesting what concerns light fibs, right? So for the neutrinos, again, I argued that the Mariana mass can be low, but there's no reason why it would be. For the Higgs portal, it's a real scalar. There's absolutely no reason why it would be small at all. For the hidden photon, if you assume there's some new sector, you have some nice new UV theory, and there's a mechanism, a Higgs-like mechanism that gives a mass to this new photon, then this gauge coupling that is responsible for the separation of scales of the mass of this new guy with the rest of your sector is also the parameter which enters the mixing with the standard model photon. So there's one parameter that separates this particle from the rest of this sector and that suppresses its couplings. So this is precisely what is meant by fibs if you want to look for light masses, right? There's a mechanism why small masses should correspond to small couplings in this kind of theory. And furthermore, the coupling structure is protected by gauge symmetry. So you are not gonna have large new couplings generated if you run down the scales. If you probe this at the low scale, it tells you a lot about the UV theory. So how do you find a new vector boson? I'm again just showing you some examples before I go to the summary plots. So one way you can do this is to go where you have a lot of statistics. You produce many, many photons, you have a high chance to produce one of these guys. And an experiment that will produce a huge amount of statistics is the mu3e experiment, looking for the muon decay into 3 electrons. And that is also sensitive for the decay into 3 electrons and 2 neutrinos through, for example, the radiation of such a new hidden gauge boson. This has been worked out for prompt decays, and people are looking at this for displaced vertices again at the moment. Now, LHCb has huge statistics as well. They have 14 trillion D star mesons, and there's a very nice paper from 2016, Philip Ilton et al., that have proposed to look into these decays. You basically count the number of D star to D gamma decays and D pi as well, because the pion eventually is going to give you photons too. So this particular excited state decay produces an enormous amount of photons potentially. And each of these photons has then a chance to mix into this dark sector. So they will both be very sensitive. Here's the summary plot again. It's again very busy, but and it's probably harder to see, but you see this purple contour here. So in this kind of gap between collider experiments and beam dumps, mu3e will cut with its search, and the D star to D gamma search goes along the line of this shape here. Again, it's hard to make out, but it will eat deep into this gap and see whether there are new states there. And there are other searches like the inclusive muon resonance search at LHCb that is shown in gray here, and resonance searches at CMS for higher masses too that I didn't have time to talk about. But they all constrain this mixing parameter epsilon over there. Now, there can be different variations of this story. So the coupling and branching ratios changes a lot if the new gauge boson does not only mix with the standard model photon, but actually some parts of the standard model are charged on this new U1. And that is possible for a limited number of charge assignments. I've written the groups here that you can get and combinations thereof. Anything else requires to throw more matter in to account for anomalies. And in some of these models, depending on their structure, in particular for the lepton family number differences, you will actually be able to calculate the mixing parameters because the calculation does not depend on some scale beyond the masses of these leptons. And that has to do with the way they are embedded. So that you can basically write these groups as a direct product with the standard model, which is not possible for B minus L. And therefore it has some additional sensitivity to the UV scale. But that is nice because now it is not a completely free parameter anymore if you assume some embedding like this. Now, you would be smart to ask why I haven't talked about these flavor constraints here. I mean, LHCb again can play an important role, but these B to K constraints, which were really, really important for the scalar portal and the kaon decays, which were really important for the neutrinos, seem to play absolutely no role. And together with Patrick Follner and the student Martin Mosny, who just now starts his PhD thesis, we have actually shown this projection here and explained why this is. The gauge symmetry protects these couplings such that they need to go to 0 if the mass of this new guy goes to 0. Then you have a perfect gauge symmetry, and they need to vanish if the mass of the internal quark is 0. So there's an additional suppression with from the GIM mechanism, such that these constraints are really, really, really not relevant for these types of new gauge bosons which couple to the standard model, not just through mixing. Now you can say, why I'm going to tell you this, because that just means don't look at that, but that's not true at all. So there have been some nice papers by Dror, Lesenby, and Maxime that have shown that, of course, this argument doesn't hold anymore if your gauge symmetry is not a gauge symmetry but anomalous. Then part of these diagrams that contribute to these loop functions are not in place, and then these constraints can be really, really important. So you can turn this around and phrase this as this would actually be able to tell you whether a new vector-like state that you're looking for is a gauge boson or is maybe a composite state that doesn't follow a gauge symmetry. So it's really important to look for them. It's basically a discovery channel for anomalous structures. Here, again, things can also look very different if you not just charge something in the standard model, but you have some dark matter that dominates your branching ratios. So imagine the vector is coupling to some dark matter particle, and that dark matter particle is 99% of the decays of this new photon. Then it is really hard to see. It's just an invisible decay. And again, a number of new experiments like LDMX at CERN, for example, will go orders of magnitude beyond what we have seen so far for this type of new one. Finally, let's move on and discuss the axion portal. So the axion portal, you could argue, has really no place in this list because it's not renormalizable. The other portals are, and the axion portal starts at dimension 5. So any operator that couples the axion to the standard model starts at dimension 5. And there's a good reason for this, because axions or axion-like particles are really a not so good name for pseudo-number Goldstone bosons of some approximate global symmetry in the UV. So whenever you have some spontaneous breaking there, you get a relic, and that is this state at the light scale, which you could call an axion. So they correspond to the phase of a complex scalar, and because they are the phase of the complex scalar, their interactions are protected by a shift symmetry. Right? I can always shift the phase by constant, and that doesn't change the physics at all. That just gives me gives me a phase. In other words, this degree of freedom corresponds to moving around this potential, and there's no friction there. Now, that also produces a completely massless boson because the mass term breaks the shift symmetry. But that's very problematic. A completely new massless boson would be strongly constrained again by these equivalence principle constraints. There would be no reason to look for it elsewhere. But the global symmetry can be broken by explicit masses or anomalous effects. And if you have such an explicit breaking, you usually get a small mass that is suppressed with the same scale that suppresses the out couplings coming from the fact that it corresponds to that phase. So even though it has non-renormalizable coupling, this is a very similar mechanism to the gauge boson for good reasons. Again, we have a model where if the UV scale is displaced by a lot, for example, out of the reach of the LHC, that and it includes such a Goldstone boson, that means it would be very light and at the same time very weakly coupled. There's a mechanism that relates small masses to small couplings. Now, the most famous example is the pion. Like QCD has a large global symmetry. You can rotate left and right hand quarks separately. And there's a small explicit breaking by the Higgs vector. And now you have the breaking by confinement. And the pion mass is therefore controlled, just like I showed you before, by a combination of these two effects. And the explicit breaking sets it apart from the scale of the other resonances. Now, the fact that this is an order of magnitude in the QCD spectrum is just an accident. If the up and down masses were the neutrino masses, we would have a huge separation of scales there. And the couplings of the pions would be pretty much unchanged at this point. So we can easily imagine that we have a new sector at a very high scale. And because the explicit breaking happens to be not very large, that all we are left with is this light axion-like particle that we can look for as our Phipps candidate. Now, the most general dimension 5 Lagrangian that encapsulates all these couplings has been written down in the 80s. This extends the QCD axion, which would just include some couplings there, in particular the coupling to the gluons. But in general, every shift symmetric coupling is allowed at that order. And depending which couplings exist, the branching ratios of an axion can vary significantly. So I'm showing the summary plots from the Phipps report again. In this case, for the couplings of the out2 photons, you can see a similar structure. You see some collider limits from Bell. If you would go further to the right, there would be LHC limits as well. And you see this huge potential of the new displaced vertex searches creeping up here as well. If instead you have an axion that mainly is produced through couplings, this plot extends below to smaller masses too. So the QCD axion here, the QCD band would be somewhere up here. It's basically excluded for all these masses in this plot. But if you go to very low masses, you see that it comes down here. And there is actually parameter space that is not excluded yet. And that again relies on assumptions too. So this QCD axion band depends very much on the structure of the strong sector at very high scale. So if it's not just SU3, but you have some enlarged color groups up there, then this could shift quite dramatically in this parameter space. But again, it shows the complementarity. Some general axion-like particles with masses in reach of the LHC ends up here. And you have these haloscope and other searches that constrain light axion-like particles. Couplings to gluons is another benchmark point proposed by the Phipps working group. This looks dramatically different. If the couplings to gluons dominate, you have all these mixings with through the chiral Lagrangian with all these mesonic states that lead to these mesonic decay channels becoming very sensitive. But again, displaced vertex searches are important to constrain this parameter space further. This plot shows this shows another coupling structure. Sorry, this was the coupling to gluons. This is the coupling to fermions. So this shows dominant couplings to fermions. So you also have mixing through the chiral Lagrangian with the mesonic states, but you have other experiments that are also sensitive in the high mass region. Now, unlike a vector boson, the ALP coupling structure is really not protected by symmetry. So the running of the general ALP Lagrangian has just recently been worked out by Miki Challa and others, and also in the paper by Matthias Neubert, Sophie Renner, Marvin Schnubel, Andrea Tam, and myself. And it shows that there is a lot of mixing and running involved. So all these parameters are generated if you start with a given coupling at the UV scale, and the UV scale here is just 1 TeV. So in particular, if you have, for example, a coupling to top quarks, you really get large couplings to pretty much every standard model fermion at a low scale. And that is kind of an unexpected effect that comes from the mixing of the ALP with the longitudinal mode of the Z boson induced by the operator down here. Now, this is also dimension 5 operator. I haven't shown you before. And the reason is that that operator can actually be removed by the equations of motion. So it can be mapped to the fermion operators. It's still relevant as a counter term in the running. It also has some further relevance because this particular operator can give rise to a coupling of the Higgs to the Z and the ALP. So how can that be if it vanishes by the equation of motions? Well, it doesn't generate this just by its coefficient, but it does generate this decay if you have some ALP couplings to fermions in the loop that get their masses from electric symmetry breaking. So you can basically treat the Higgs as a background field here, and you get this non-polynomial version of this operator, which generates this coupling at dimension 5. It also exists at dimension 7, so you also get dimension 7, but that would now be suppressed with this new scale cubed. This is not completely new, this kind of behavior. Aaron and Lian Tao and Jesse Taylor have a very nice paper where they show a very similar effect in di-Higgs production. But in di-Higgs production, it just makes a difference in the distribution, whereas here, it basically decides whether this channel is present or not, because it's generated at dimension 5 or not. So if you observe this particular decay, first of all, it is sensitive to the quantum numbers of the axon, because the axon is a pseudoscalar, and the longitudinal mode of the Z boson is a pseudoscalar as well. But also it tells us something about the UV structure of the theory. If the theory in the UV includes fermions with a large part of their masses coming from electric symmetry breaking, you get this at dimension 5. If it doesn't, you don't. So it's really, really important to look for this particular decay, and also has very nice experimental implications. So consider 3 different masses for the axon here. Imagine the axon is very, very light. Then it's produced with a high boost in this particular decay. That boost can be so high that the 2 photons cannot be distinguished at the LHC. So what you then get is basically an enhancement of Higgs to Z gamma, because the LHC wouldn't be able to tell apart these 2 photons if they hit the same calorimeter cell. So that would always be enhanced because there's no interference, and that would be a prediction of such a light ALP. If the coupling is small as well, and the mass is in the medium regime, then you could see this ALP decaying into 2 photons, and you have a new exotic signature. Higgs goes to Z and 2 photons, which is resonantly enhanced. So it's again a very nice way to search for this particular particle. And if you have very, very small couplings, then it becomes even more challenging, but that could be a task for the future kind of experiments I've shown you before. Imagine the Higgs decays into a Z boson, and the ALP does never decay inside the detector. These Z bosons would be lost. The LHC collaborations wouldn't count them because they wouldn't be able to ever figure out that it came from a Higgs. But if you were able to get the ALP from this decay at some far detector, and you wrote to tape all the Z's that you have down here, then potentially you could see and discover this decay channel in this very exotic signature. Now, a last point I want to make relates to a model that I really like. And that is, if you increase the amount of symmetry, you can get around some of these limitations that you get, for example, from the different decays that are induced from the running. So if you increase the symmetry of the Lagrangian that already has a shift symmetry, for example, by a simple Z2, then all these operators vanish, because if the ALP follows a Z2 symmetry on top, then you need derivatives and an even number of fields. And then the leading operator becomes the Higgs portal. Now, the momentum suppression of this interaction leads to considerably weaker constraints from BBN and fifth forces and spectroscopy that I've shown you before. In fact, what you get is something like you see on the right-hand side. You see that Higgs to invisible, of course, is still by far the dominant constraint, but basically all the other constraints fall away for low masses because they are experiments measuring this kind of new particle at very, very low momenta. Now, there are also experiments that rely on the fact that you have linear interactions, for example, light shining through a wall. So also these kind of experiments would not be sensitive. So what could you do in such a case? Well, we figured that actually if it couples to the Higgs portal, you can't do any better than Higgs to invisible. That's basically the one observable you would have in that particular case. But if you have another mediator that is not the Higgs, like some new scalar phi, for example, that still follows these same rules, then the Higgs portal constraint falls away, and then this parameter space is really almost unconstrained. At the same time, you now have an out that is protected by Z2 symmetry on top of the shift symmetry, so it's a really good candidate for dark matter. It basically can't decay, even if it ends up being heavier than it would need to be for stability from the shift symmetry. The LHC would still produce these things a lot, given that it can produce phi, which we have enabled through the coupling to the gluons right here, right? So what could you do? Well, if you had dark matter of this kind, many experiments would be blind to it, but the LHC could still see it by acting like a direct detection experiment, pretty much. So what could happen is this phi could be produced. It would decay into pairs of these axion-like particles that travel through the detector. They never decay, but if the interaction is strong enough, such that you produce it copiously at the LHC, it can actually scatter inside the detector. So what you would get is deep inelastic scattering of this new particle of some detector components, because the density of detector components will basically guide whether such a scattering process is likely or not. So in the inner part of the detectors that are gas-filled, you would never see something. But in the very dense part of the detectors, you would have the chance to, from time to time, see events that look like displaced jets, but are really scattering events of this type of dark matter with the detector material. And we show in green here what you could do at the high Lumi LHC in that case. Let me give you my final remarks instead of a conclusion. FIPS are an enormously active and growing field, as you can tell from all the different signatures and models I've presented here. This is also a young people's game. So basically all the ideas, the models, the new detectors that need to be built and proposed in this talk have come from young people. And CERN has signaled support for this new activity. They plan for a FIPS physics center, of which I can say nothing beyond that. I can show you this graphic, which was shown by Gaia yesterday at the PBC workshop, that there's some implementation in the PBC working group. It's the PBC's portal towards the external world. I don't really know why they need a portal to the external world, but that is what is envisioned. There will be more to hear from that soon. And with that, I thank you for your attention.
Thank you, Martin. Very nice talk. Kingman, you're again there to moderate the questions, right?
Okay. Very nice talk, Martin. And there are quite a number of portals that you talk about, and now we are open for questions. Questions from the panelists and questions from the audience.
There's a question from the audience in the Q&A box.
Yes. So Oliver, you will unmute him so that he can talk?
Yes, I will give this person the opportunity to speak up. Otherwise we'll just simply try and read out the question loud.
Okay, the guy, Nico Muxino.
Hi, hello there. Can you hear me?
Yes.
Yes.
Okay, thank you. That's also a very nice talk. So just curious if when you talk about this vector portal, if it's possible in any way that we see any sign or look and sign of this vector portal at Atlas or CMS in the high luminosity LHC.
So Atlas and CMS for sure dominate the high mass range there, right? So I've mainly focused on lower masses, but if you approach the Z threshold or even beyond, there's really Atlas and CMS are the only places that can produce this thing, which would basically look like a resonance, right? So you can do resonance searches, and again in Higgs decays potentially. So Higgs to Z gamma, depending on the coupling structure of this new particle, can also be a target. Higgs to the gamma prime, I should say.
Thanks.
Okay. And I see a hand raised up from Dave. Dave, you can talk.
Hi, Maureen.
Hello.
Nice talk.
Hello. I have a question. Is it possible that the pi-zero meson mix with action?
Yes, that's definitely possible. So in fact, we had a paper out just yesterday that corrects a missing contribution to this particular mixing. So there isn't a chiral Lagrangian mixing between all the pseudoscalar mesons with the axon-like particle. And depending which things you turn on and off, this is a very important effect.
Then at LHC, many pi-zeros are produced, pi-zero meson are produced. Then it can convert into action by mixing. Then there could be some such signal in LHC experiment, I think. Do you agree? Do you agree?
Typically, the dedicated experiments are better at constraining this than the LHC detectors are. But in principle, it's obviously true. Yes.
Okay. Into the now I am considering such a project, performing such a project. So,
yeah. Very good.
Yeah. Thank you. Thank you.
So I see two hands raised up. Let's see, how do I do that? Dave, you want to talk now?
Okay.
Yes.
Hi, Maureen. So I had a question on your lepton portal summary plot. If you could just go back there.
Yes, of course. Give me a second. Which one of them? There were three.
You can go to the electron one.
The lepton portal electron. Yes, here we are.
Okay. Yeah. So I see some of the important constraints missing here. So I would like to know why they were omitted from this plot. First of all, the Newton-less double beta decay, that gives the strongest constraint in most of this parameter space. Unless, of course, you assume that this is just a Dirac neutrino, then you do not have that constraint. But I see in the high energy region, you saw the Atlas and CMS constraints in the top left, in the top right corner. So that is only valid for Majorana particles. So I'm wondering why the double beta decay constraints are omitted from this plot.
So I have to refer you to the FIPS report. I have not worked on this particular constraint, but and I don't want to say anything wrong, but I believe what you say is absolutely right. This is a very strong constraint in much of the parameter space, and you actually have to do some tuning to get away from it. But again, please check with the report on this particular constraint.
Right, and also I think the electric precision tests put very strong constraints, especially in the higher mass range, because they're independent of the mass. You just take the effective operator, and then that affects a lot of precision parameter, like the I think for example, the muon decay, extraction of G Fermi, and then also the sine square theta W, and so on. So all those put a constraint. I think it's at the level of 10⁻³ to -4 in the higher mass range, and that should also be included, I believe.
Yeah, so I thank you very much for the comment. I cannot argue for the details of this plot, unfortunately, because I have not worked on the lepton portal directly. But I'm happy to forward this comment for sure.
Okay. Another hand raised up by Rohini. Rohini, you can go ahead.
Thank you, Kingman, and thanks to both the speakers for very nice and detailed talks. I actually had less a question and more a comment on the LLPs. So if somebody wants to discuss more Martin's talk first, I will wait and I can make my comment about the LLPs later. So if there is no other hand, then I can go and make my comment just now. Kingman?
Yeah, how about we wait maybe 1 more minute? Any
because
question to
unrelated
Martin?
to Martin's talk.
And then, yeah, and then we go to the more general discussion about the hidden signature at the LHC. Yeah. Any more questions? Oh, by the way, Martin, I have just a very quick, simple question for the
I have
FIP
also flagged the question. I have also raised, right after Rohini, I requested a chance to make a comment.
Okay, let me just ask a very simple question first. The FIP center proposed is model oriented or signature oriented?
It is a very good question, and I can't answer it because the proposal and all these details have really just surfaced yesterday. So I wanted to mention, because the organizers asked me to also talk a bit about organization, but this is still very young, and I don't have any details yet. What I can say for sure is that one of the goals is to get a closer collaboration with theorists and experimentalists on these particular topics.
Okay, good. Thank you. That's a very exciting area now. Okay. Any more question particular to Martin?
Yes, as I said, I have a comment for him.
Okay, yeah, yes, please go ahead.
Thank you. So, of course, it was a very nice talk. I would just like to draw everyone's attention to a related scenario where you have long-lived particles, but where they don't decay within the detector. But in the dark sector, there is the lightest particle whose coupling with the next to lightest ones is incredibly low, small, so that the signal of dark matter is not missing ET, but long-lived stable charged particles. Now, this is a scenario supersymmetric as well as non-supersymmetric, where we have been working for more than a decade now with various collaborators as well as in my own group. Well, in the non-supersymmetric context, there can be such things, including higher dimensional operators involving the Higgs and so on. But I would rather like to, in this brief comment, remind you that in a supersymmetric scenario where you have right-handed neutrinos and their corresponding superpartners, the Wright's neutrino has very strong candidature for being the LSP and a dark matter candidate. It's a feebly interacting non-thermal dark matter. But the catch here is that the next to lightest supersymmetric particle, for example, the lightest tau, that decays in an excruciatingly slow way to the Wright's neutrino dark matter. So supersymmetric search paradigm is completely changed here. You have supersymmetric signals with the help of, look for supersymmetric signals with the help of long-lived charged particles. There has been a lot of work, and we have done a lot of work as well. And constraints are there, not in the context of Methuselah and Anubis and things like that, but in good old LHC itself, constraints are derived. But the point is that here, supersymmetry search paradigm is not only changed, but also, for example, we showed in a paper about 2-3 years back, together with the NSC group, that in this scenario, you can revive the M-Sugra type situation, which is highly disfavored in the present context, in the context of present data. You can revive it, and you can have an M-Sugra type and CMSSM with only a Wright's neutrino mass parameter inserted. Of course, in this kind of scenarios for supersymmetric as well as non-supersymmetric models, the strongest constraints come from freeze in, freeze out hardly poses a constraint. But as far as collider searches of such scenarios are concerned, both taking M-Sugra type things in view and just pure phenomenological MSSM augmented by a neutrino field and also non-supersymmetric context, a number of very interesting predictions can be made and constraints can be made, which may be relevant in the context of the high luminosity LHC. Well, that's all I wanted to say.
Okay, thank you. Thank you, Biswap.
Martin, do you have any comment on this? I would like to
learn. Yeah, so I should say, so that's a very good comment, and I should have said this also during the talk. These portal structures and what I discussed, of course, was a selection of what is possible for feebly interacting particles. I said that I'm going to focus on live particles, but it was of course not even comprehensive in that context. Beyond what you just said, which like long-lived charged particles, Susanne talked a bit about this as well, is a very striking signature, but there are also microcharged particles which you can get and search for at the LHC, which I have omitted in this talk. So because of time, I had to focus on a selection, but you're absolutely right that this is something that should be looked for as well. There's no reason why it wouldn't exist. And actually, like you mentioned, there's quite some well-motivated theoretical scenarios in which you would see this as your main signature.
Okay. Okay, thank you.
Okay, now shall we go into the Hi.
Yeah.
Oh, so we are now going to the general discussion. Please go ahead.
So I would like to make my comment by saying that it's somewhat in the line with what Vishwarup was saying. What I was saying is that one can have heavy particles which are long-lived, say, for example, in supersymmetry, where there is very complex spectrum. And if these guys, this is a very interesting LLP scenario, which some of us, again, with the NSC group and one CMS experimentalist, we had studied. And this had to do with the fact that if the particle is very, very heavy, then it's moving rather slowly. And when a heavy particle decays slowly, some of the decay products actually get thrown back. So if this, say, heavy LLP decays, say, in the tracker, then you have these non-pointing tracks, if you wish. Then if this guy decays even outside the, let's say, muon chambers, again, some of the particles will travel back. And what we had shown that since this is a pure kinematic effect, you can actually see that there is a largish fraction of the decay products, which in fact comes back quite often. And this would be a completely different way, what I would call backward moving objects. That the LLP is produced, it moves in the form, of course, as usual, away from the interaction points, but the decay products get thrown back. And this is an entirely different class of LLP ideas, which one can maybe try to see along with more, this discussion with experimentalists, because again, this is in the good old SUSY, these situations can very easily arise. Though this has no dark matter connection, and that's why I was making this statement separately.
Yeah,
so I have made my comment.
Yeah,
I would like a responsive.
Yeah, Rohini's comment is very valuable because I am familiar with this work and which is done sort of parallelly. An interesting feature here is that the LLPs, since they won't decay within the detector in many cases, they will be likely to be faked by ordinary standard model muons, which have a huge background and which also come from cosmic rays. So a number of devices have to be made. And one of them is that what has been shown is that this is a kind of situation complementary to what Rohini suggested, where the particle, the more massive the particle is, the long-lived charged particle is, the better is the selection criterion in terms of time delay between the tracker and the muon chamber. That has, yeah. Rohini, you probably agree with this statement.
Yeah,
right?
yeah, no, I go ahead. I mean, I just wanted to bring this for the discussion to and bring it to the attention of the community that there is this entirely different type of LLPs decay possibilities which are not necessarily implied by dark matter paradigm. That's all I wanted to say.
Okay, okay, I completely agree with that.
So very good comment. I wonder, do you know whether hadron searches constrain?
Yeah, that is actually true, and this can actually, this can actually be relevant even in the hadron searches.
Yes,
and that's why actually I wanted to make this comment.
Yeah.
And what it needs, however, is a detailed understanding of the detector. because here now you have to think how one understands a shower created by a backward moving particle, for example. Or as Bushwarup suggested, how does it work? How do you separate these muons or the backward moving objects from cosmic muons, the hadrons that are generated from cosmic muons? So I think much more work needs to be done. But all I was saying is that this is a pure kinematical effect, in fact.
Exactly.
And therefore might be sort of, completely free of, in some sense, models, but at the same time, something that can naturally occur just because of the pure kinematics. And it might be nice to have the discussions on such things in some forum, so that we can increase what we can see.
Yes, thank you, Rohini, for such a very interesting way to see the LLP. Yes, certainly this is a very good way, very new kind of signatures. Yeah, I see another hand raised up by Nishita. Nishita,
yeah,
you can talk.
Yeah, thank you. Yeah, so I just wanted to comment on what Rohini was saying. So one of the things that the experiments currently do is they rely on having a primary vertex to sort of ascribe what tracks and things you have to a particular event. But in your case, where you have the particle decaying far off and the tracks coming out of time, how do you make sure that, I think, wouldn't you run into problems with triggers and so on? How would you
No,
make
so one will
sure?
have, that is the whole point here, that you will have to see whether one can catch these things, and one will have to work on triggers for that also. But the point is that what we show is that pure kinematics tells you that quite often a very large fraction of the decay products will be doing it. So, and if we don't figure out in conjunction with our friends how to do it, this will be lost. And in fact, our CMS friend on the collaboration had shown a few things that could possibly be done, but it needs much, much more work. What we had was a toy.
Right.
We were just
And
looking at a toy.
also, so there are two cases, right, where the original particle is either charged or neutral. If it is charged, of course, you have the charge track, so I won't talk about that. But if it's neutral, then you would still have a missing energy signature, wouldn't you? So it's not nothing. So you could probably have
we
some
can talk more about
yeah.
it, Nishita. I would be very happy to have more discussions on this, because what stopped sort of the discussions, because precisely the first question you asked is we needed to understand how the detectors do something. Particularly the inner detector. Okay.
Right.
And because if it's a compressed spectra, there is not necessarily that much. We can discuss it, because if it comes back, it may not be counted as missing energy, right? Again, if there is, it's a non-pointing thing, and one has to really see what it's meant by non-pointing hadrons.
Okay, audience, I think we can make more general discussion. The question can also be addressed into the previous speaker, Suzanne, and also to any of the panelists. Yeah, I can see Suzanne raise up the hand. Suzanne.
Yes, I have another comment to Rohini's idea of backscattering particles. We recently analyzed that for the Day2 experiment, also the complementarity was missing energy signature. So I think such a discussion, if we want to follow up on that, would be valuable in a broader framework, right? That looks more broadly at backscattering and colliders beyond the LHC as well.
Okay, great. I will be happy to see such a discussion. Thank you.
I think some of the insights that we got for Day2 might apply to the LHC.
Fantastic.
The environment is of course very different, but I think it would be
fantastic. That was the reason for suggesting this. Fantastic.
And yeah, I have a question for Suzanne. In the co-scattering scenario, how sensitive is delta M, the mass difference, to the relative density?
So the sensitivity is high, it's exponential basically. I mean, it's incasted in the final abundance, but what is essential for co-scattering to be effective during the time of freeze out is really the number densities of dark matter and its partner, right? So if you want to upscatter into a heavier state, you can only do that at finite temperatures. And this means that the heavier state should not be much heavier. Otherwise, its abundance, since it's Boltzmann suppressed, has decreased too much. So there would be basically no efficient forth and back co-scattering. And this would mean that co-scattering would become irrelevant for setting, for determining the number density of dark matter. So this means that this mass splitting, there's some variation in it, right? So it depends a little bit on how the hierarchy of relevant scattering and annihilation processes, decays can also matter. So there's different dynamics that can contribute, and depending how they relate to each other, co-scattering can be more dominant or can be one of several processes setting the relic abundance. So this means that the mass splitting is not cast into stone, but it's a matter of fact that the ratio of dark sector abundances exponentially depends on it. So this makes the prediction strong within a certain model.
I see. So it's very similar to the co-annihilation scenario, right?
It shares some aspects, right? So it's often that models that feature co-annihilation would also feature co-scattering. But the main point is that co-scattering for a fixed set of fundamental interactions and the fixed spectrum, co-scattering in the early universe is always more efficient because scattering happens off a bath particle. And this bath particle is just more abundant, right? So I think it's easy to understand that there's just more chance for a dark matter particle to scatter off a massless bath particle than of a massive state from the dark sector. That would be the case for co-annihilation.
Okay, thank you. So there's a chat. What is that? It's noise on speed. Okay. So there is a question in the chat room. It's very noisy, so I won't speak. I just type my question here. Please read it out. So the question from Suchita is that given the signature portal-based approach for long-lived particle surges, is there a lower limit on couplings when we decide to give up on a specific portal or signature? I think the question perhaps addressed to Martin. Martin, do you see the questions on the chat room?
Yes. Can you hear me?
Yeah, yes, I can.
So I think
anyone can answer, yeah.
Yeah, I think it very much depends on the portal, but in most cases, there is a limit for which we know that there is already everything ruled out in this parameter space. So if you look, for example, for the Higgs portal, if you go to very low masses, and everything you can potentially do with a collider is basically limited by this BBN bound that is so strong that a collider surge can potentially compete. And that also corresponds to a decay length. So for example, initially an experiment like Mafusla was motivated by the fact that you want to measure, I mean, you could ask, why don't you build it 1,000 meters away or 10,000 meters away, right? You want to target decay length that fall between the BBM limit and prompt decays, ideally. So for this particular scenario, this is the limit. But for other portals, it really depends on what we know about this. I would not really see it like as a lowest possible coupling or the longest possible lifetime that is excluded. There's more like a patchwork. In the case of the Axion, for example, for heavier masses and very low couplings, we have really strong constraints from CMB and other cosmological sources. And if you go to a bit lighter ALPS, if you look at the summary plot, then you see that the parameter space is wide open. So I think it really depends on the particular scenario. We want to test everything we can test, I would say, at the LHC.
Yeah, maybe to add to that, so specifically at the LHC, there can be different ways for the lifetime of a particle, right? Then its interaction strength. So there can be a kinematic suppression of the decay if it decays to particles that are just a little bit lighter. So that happens, for example, for co-scattering. But there can be other ways, right? So the decay can be protected by symmetry. And I mean, you might translate that into an effective interaction strength. But then the question is still, what does that tell you about the strength, the fundamental strength of interactions in the new sector that you're looking for? So I think it's difficult to translate like a lifetime search or displacement, like the observation of a displacement directly back to the fundamental Lagrangian and to the fundamental interaction strength. So I would not restrict the range in any way.
Any more questions from the audience? Oh, okay. I have a question for Martin about the scalar portal, about the ultralight axions 10 to minus 22 eV. I mean, this is given by the cosmology frontier to solve the small scale problem. How would we test this axion in any way to test it in collider? Or
one way is that doesn't apply for these extremely small masses, but one way that extends to very small masses is the last model I presented. If you have, in particular for axion-like particles, if you have derivative couplings, then all interactions are scaling with the momentum of these particles. And then if they hover around in the halo, right, a direct detection experiment is absolutely blind. These are way too light to have any momentum transfer that can be seen. Indirect detection is also blind, because what you produce would be, even if you have a large coupling to photons, the kind of photons you produce are so soft, no satellite would be able to distinguish this from the backgrounds. But in particular colliders, because you can produce large momenta, if you can produce these particles at colliders, you can actually give them the momentum that is necessary to scatter off something like a collider component. So these are exotic signatures that are not necessarily possible for other kinds of dark matter, because the parameter space is completely ruled out. But in general, colliders have this particular feature that they can produce things resonantly and with a large momentum, and you can use to probe particles of any mass, right? It doesn't matter then anymore what kind of masses they have if they are produced with a very, very large momentum.
Okay, thank you. Do I see more questions? Anyone raise hands? Okay.
So I don't see more questions. Maybe I can come in. Thank you, Kingman, for leading the discussion. Sorry, I cannot raise my hand. Actually, I don't think I have that option. So thank you very much for leading the discussion session. And also thanks both the speakers of the first session, Martin and Susanne, for great presentations, and everybody who had nice questions and discussions. Before we go into the break, I want to leave all of you with a question. So we have now had one technical discussion on long-lived particles that was really on the details on how you would see a certain signature in a given detector with given technical limitations and non-standard model backgrounds that could fake the same signature. If you had the opportunity to design your own search, how would you do that? Assume you have all access that you want to all subsets of the data. Would you be able to come up with something that's better than what the collaborations do at the moment? And do you think it would be worthwhile to pursue? This is my closing remark for the first session, because Susanne made this comment that we should always see if we cannot really exploit the data that we have. So think about it, and then we'll be back in 25 minutes. Now we can go into our break. Thank you very much.
Thank you.
Thank you guys for wonderful talks and discussions.
Thank you. Thank you.
Okay.
Thank you to both the speakers for the very, very nice talks.
So welcome back from your coffee breaks or whatever you had. So I enjoyed my coffee. And after the first session that was on hidden signatures, now we move towards models and machine learning. Machine learning and tools. Let me introduce you the next speaker, Kai Krenmer from the New York University. And what I found interesting when I looked up his affiliation to just verify I'm not saying something stupid, he's also affiliated with the Center for Data Science. So I think this is a sign of the times that you are living in. So Kyle, if you're ready, you can share slides and you can start giving your talk.
Great. Can you see me and hear me fine?
Yes, to both.
Okay, great. Yeah, that's right. I am in the physics department, also in the Center for Data Science, and then also the Silver Lab is the kind of core machine learning group at NYU that includes Jan LeCun and company. So it's and Kanyan Cho and Joan Bruna, who kind of well known for their work in like graph neural networks and recurrent neural networks and convolutional neural networks. So I'm going to be talking about machine learning for precision measurements. I just lost my timer that I was going to use, but okay, hopefully I'll do okay. So I'll like to acknowledge just the fun group of people that I've been working with on this. So well, you just heard from Tillman, Sally, and Sam, who worked together with Johan and Felix on some studies that I'll show. And then on the top row have been people that I've worked with kind of more closely on developing some of these tools and techniques. Okay, so the topic that I wanted to kind of pick in particular was about essentially making precision measurements and how we can use machine learning to do that. And it picks up very much on what Tillman was saying about inverting the simulator and things like that. So what I'm thinking about is that we have this very high dimensional complicated event data from the LHC, and we would like to turn that into constraints on new physics. And for the purpose of this talk, I'll just focus on when the new physics is sort of characterized with an effective field theory. It could be something different, but that's what I'll work with here. So that effective field theory, have essentially the standard model plus some additional terms. You have these higher dimensional operators that parameterize the effects of physics, and they have some coefficients out in front. And if all those coefficients are 0, then you have the standard model. And if you see any of them being non-zero, then you have signs for new physics. Okay, so this is one of the flagship measurements at the LHC. So there's a lot of people working on it. And at Higgs 2020, there were several talks. And here I just grabbed a nice talk from Saskia Falke, who's talking about different strategies and the sort of trade-offs between, kind of highly optimized analyses, which is largely what I'm going to be talking about, versus approaches like fiducial and differential cross-section measurements, and differential or quasi-differential approaches like simplified template cross-sections, and the sort of trade-offs. So one thing that I'm not going to talk about here is that when it comes to the point of trying to reinterpret these searches and the model dependence, much of that can be solved through other technical means. So we have some other work going on under the name recast and efforts to, for instance, publish likelihoods, which connects to a subject tomorrow, which we've been working on a lot to try to really handle the kind of technical problems about how the field reinterprets. But once you pick a model and you want to interpret within the context of that model, I'm certainly a fan of sort of highly optimized approaches. Okay, so now, but I think, independent from the reinterpretation issue, the bigger issue from my mind for the simplified template cross-section approach is that it's not really exploiting as much differential information. It's not looking at all the kinematic distributions. So if those approaches only lost a little bit of information, then maybe it would be worth it to have something simple. And so the question is, is it really just losing a little bit of information? So this work from Sally, Sam, Felix, Tillman, and Johan that looked into the simplified template cross-section approach. So here it's looking at associated production of a Higgs. There's 3 different production modes. And for each of those modes, you're breaking it into sort of 0, 1, and 2 or more jets. And then also regions in terms of the PT of the vector boson. And so now you have sort of, you're just, counting events in these different regions, but it's, laid out in phase space in such a way that you have, some sensitivity to the EFT coefficients. So here they considered 3 different higher dimensional operators and looked at this particular process and then looked to see, how well is it doing compared to what you could in principle do. And this was the result. So the red ellipse is the sort of expected limit that you would get using simplified template cross sections. They considered a kind of improved approach, which was the green. If you use two-dimensional, like fully differential information, or not fully, a two-dimensional, doubly differential cross-section approach, you get to the dotted line, which is quite a bit better. But then if you use the fully differential information, you get to this blue contour, which is like, dramatically more precise for one of the, big flagship measurements of the LHC. So in my mind, this is kind of like, very strong evidence that we should put more effort into trying to get at these, this fully differential information when trying to do these EFT parameter measurements. Okay, so now I'm going to switch in kind of like the statistical approaches of how we're going to approach this. So I'm going to call theta. These are going to be the whatever parameters you want to measure. So they could be things like the EFT coefficients. And then I'm going to think about the differential cross section, sort of the, divide out the normalization constant. And I can think of that as a probability distribution for some high dimensional event data, given the parameters theta. So that is the likelihood function. And once you have that thing, you have very clear, prescription for how to set limits and things like that, find the best fit, confidence intervals and such. Now, so the bad news though, is that particle physics processes do not have a tractable likelihood function. And this is kind of a strange thing because we've been doing, likelihood fits for, decades. So what do I mean by this? What I mean is if we really look at our highest fidelity simulators, what do? They start off with some theory parameters like, Lagrangian coefficients. Then we have a hard scattering, matrix element and things in like MAGRaph, et cetera. And that gives us parton level momenta. And that's certainly very much under control. And then after that, we have the parton shower and hadronization, which while we know kind of the splitting rules, the way that everything fits together turns this into a very complicated process that we basically have to put on a computer. And then from those hadronized particles, then we have the detector simulation, which is incredibly complicated. And then we have our reconstruction chain until we finally get to the observed data that the experiments work with. And so when we simulate this, we use Monte Carlo tools, right? And we usually think of like MAGRaph, Pythia, and Geant, these event generation Monte Carlo tools in terms of like giving us synthetic samples. And that's true, but you can also think about Monte Carlo as a form of integration. So with, conceptually and symbolically, what these tools are doing are trying to integrate out what's going on with parton level inside of the shower and inside of the detector simulation to try to describe a distribution for the observed data given the parameters. And so everything that's happening inside of the simulation, the Monte Carlo truth that we can't observe, is what statisticians would call a latent variable. And so what you see here is like, that's the generative process going from right to left, and we would like to invert and go from observed data back to the theoretical parameters. So this integral that's being implemented by the Monte Carlo generators is totally intractable to actually calculate. I mean, you can sample from this distribution, but if you wanted to say like, what's the likelihood for this particular event at the LHC, you'd have to integrate over like 100 million dimensional space for that one event, and that's just never gonna happen, okay? So this is an intractable integral. Okay, so what do we usually do? We usually simulate this high dimensional event data, and then we compress it down into a single observable or, the distribution for a single observable, or again, what statisticians would call a summary statistic. And so we might just count events, or we might make like a bin histogram like this, okay? And if you think about what's going on with like the counts in this bin, you're counting up, the simulated events. So that's the integral that I was talking about, right? So the problem with this histogram-based approach is that you can really only histogram events in kind of 1 or 2 dimensions. Once you go beyond that, you need so much Monte Carlo to fill the histograms. It's just not really practical anymore. Okay, so our traditional approach, if you abstract it, you have parameters that go into a simulator. They come out with high dimensional observations, the high dimensional data. Then you calculate some low dimensional summary statistics or observables like PT of a jet or invariant mass or something like that. Then we do classical density estimation like fill histograms or something similar. And then based on this approximation, so that's why I have a hat here, P hat of the summary statistic X prime given the parameters theta, then we do, well, we are going to do inference. So we also do the same thing with the observed data. We calculate summary statistics, we put it all together, and that's where we do inference. Now, the problems with this pipeline is that, one, when we calculate these summary statistics, we lose information. It's similar to what Tillman was talking about with jet physics, that those observables, they lose information. And this approach also just doesn't scale to high dimensions. And I'm sorry about the noise we have in the background here. And so it's, yeah, there's some other approaches that, that other fields use that are very similar, but I won't talk about this. Now there's a really kind of important conceptual point, which is maybe, not something that we're all taught, is that you might think, okay, well, invariant mass was like a great variable for, like discovering the Higgs. Maybe there's a great observable out there for doing EFT measurements. But it turns out you can just prove there is no observable that's good for all of the EFT parameters. In some directions, there's one observable is going to be good, and in another direction in the parameter space, a different observable is going to be good. So you can try to kind of boil the data down, but there's not going to be one variable that's going to capture everything that you want. So you really need to work with higher dimensional event data, or you'll just kind of provably lose sensitivity. So one of the approaches that the field has developed over the years is to say, okay, well, this is what we want. So let's just approximate the parton shower in the detector. And that's something like the matrix element method, where you say, okay, I'm going to lump the parton shower in the detector simulation into a transfer function. So that's what I'm calling p hat of the observed data given the parton level. And then I'll integrate out the parton level kinematics to approximate this likelihood function. You can do it. It's a bit expensive. The problem with it is that the transfer functions can be a little bit ad hoc. I mean, you can try to motivate them certainly, but they assigning a parton to an observed jet, there's that mapping is not really one-to-one. And the matrix element approach has issues when you talk about additional jet radiation or higher next to leading order and various things like that. So this approach is it's decent, but it has some kind of fundamental problems or some bottlenecks. So what we would like to have is something where we can work with high dimensional observables, including all the correlations. So something like the matrix element method, where we don't need to pick summary statistics. We would like to include, though, the state-of-the-art shower and detector models, which is not what the matrix element method does. So we want to include our most sophisticated simulation. And we would like to be able to evaluate the likelihood in microseconds, not wait for minutes or something like that, like you do in other techniques. And then finally, if we're going to use machine learning, we don't want to have to generate a tremendous amount of training data. So we would like something that's going to be kind of efficient from the Monte Carlo training point of view. So this is sort of the schematic of what we're after, is that we're going to have the parameters that are going to go into our simulation. And the first approach at this is the simulation is just going to output some observed data X, some synthetic data X, and we're going to train a neural network. But the neural network is not going to take in observed data and try to predict signal or background or top jet or QCD jet or something. It's not a classifier, and it's also not going to take in data and try to predict the parameter values of the EFT, which doesn't really make sense for one event. You're not going to be able to say what the EFT parameters are for a single event. So instead, what this neural network is going to do, it's going to take the high level, the high dimensional event data X and the parameter values as input. And then the output, we want to be approximate a likelihood or likelihood ratio. Okay, so the way that we train it, we need to come up with some loss functions that will do this for us. And so once we have found a suitable loss function, then when we train this neural network, we're approximating a likelihood or likelihood ratio, and then we can do inference and using the standard kind of tools and techniques that we have developed over the years. Okay, so this was the first approach, but this is fairly hungry for Monte Carlo. It takes a lot of training data. So what we realized later is that we can augment the training data with two things here. I'll call the joint likelihood ratio R and the joint score T, when I'll describe them in just a second. And with this augmented data that we can extract from the simulator, we can use new kinds of loss functions to train these neural networks, much more efficiently, and then learn a likelihood ratio and then do inference. Okay. So again, if we think back to the simulation chain, we have these intractable integrals over everything that's happening in the detector and the shower, which is which is difficult. But if we think about one simulated event, okay, and we think of the everything that happened in the Monte Carlo truth record, and we freeze it. Okay, that's what Z is. Okay, so we freeze everything that happened in the truth simulation and the final observable, and we think about the ratio of the likelihood ratio that says how likely is this particular simulated event for two different values of my EFT parameters. If I consider that ratio, everything that happened in the detector and the parton shower doesn't depend on the EFT parameters, so all of that stuff is going to cancel out. And the thing that you have at the end is just the ratio of the matrix element, the matrix element squared under the two different scenarios. So this joint likelihood ratio is actually something that's very tractable. It's similar to what we do when we do like PDF reweighting and things like that. Okay, so this we can calculate, and that's one of the kind of forms of augmented data. But the question is like, why is this useful? Okay, so great, we can calculate this joint likelihood ratio. But when we're doing inference, the thing that we care about is the likelihood ratio down here that doesn't depend on all of the latent variables. And so that means that both the numerator and the denominator have integrated out all of this unobserved, Monte Carlo truth latent variables. And that's not the same thing as like integrating this ratio, because the integral of the ratio is not the ratio of the integrals. So this is not clearly useful information. Okay, even though it's like clear that we can calculate it and what it means. But what's cool though is that if I think about this red curve, this true likelihood ratio here is a function of the observed data X, then this joint likelihood ratio is going to scatter around the red curve. It's not really clear how it scatters around. It's not really clear that the mean of the blue dots is the red curve, and because that would be, so it's not really clear what's going on here. But the question is, can we use that information? So it turns out that you can define this loss functional, which is a little bit weird. Okay, so it's the target data that you have depends on both X and Z. It's this joint likelihood ratio. But I'm going to try to find a function R hat, which is essentially like trying to learn this red curve, even though the training data is scattered around. Okay, and if you just use a simple squared loss function as or functional, and you find out, okay, well, what minimizes this? You can do that with calculus of variations, and you find out it's this conditional mean. Then, okay, great, but is that useful? It's not really clear that's useful either. But if you do some kind of manipulations and use Bayes' theorem and things, it turns out that this conditional expectation is exactly the likelihood ratio that you want. Okay, so you follow this math yourself offline, but this is like the magic part that makes this whole thing work, and it's really cool how it works out. And then you can do something very similar with this augmented data called the score function. So the score function is just, you're saying what is the derivative of the log likelihood function with respect to the parameters, and then evaluate it at some point. So the natural thing to do would be evaluated at the standard model. And so you get this vector of numbers out. Okay, there's one number per parameter. And it turns out that this thing is very, very much the same idea as what's going on with optimal observables. And statisticians call them, these are like the sufficient statistics. So these are like the best variables to measure, at least in the neighborhood of the standard model. The problem is that, again, these depend on the latent variables that the Monte Carlo truth we don't observe. So what we really want is the same idea where you've integrated out all of the Monte Carlo truth. Okay, so this again is, the question is, can we estimate this thing? And it turns out that basically the same trick that we used in the last slides applies here as well. So you can learn these things, and it's like learning the optimal observables, but including the effect of the parton shower and the detector simulation. So this is like, this is pretty cool. So those are the kind of fundamentals. And now if you wanted to implement all of this, it would take a while. So we spent some time and developed a tool called MadMiner. So this is mainly the work of Johan and Felix, and then Arena, and well, I've helped a little bit, but Arena has come in and tried to work on like making these things like have workflows and you can run them on clusters efficiently and stuff like that. And here's kind of a high-level overview of like, how it works, starting with kind of configuring the problem that you want, what is the theory that you're interested in, pointing to some, MadGraph model files and such, simulating data, running through a detector simulation, Here we package it up with Delphis for doing kind of pheno studies. You could in principle use the full Atlas or CMS detector simulation, but we're not going to package that up with the tool, but you could replace the real detector simulation here. And then we have this augmentation that calculates the joint ratio and score, the machine learning training components that include all the loss functions and et cetera. And then finally, we have like statistical tools that would allow you to take observed data and actually get to best fit quantities and expected limits and all that kind of stuff. So this tool's, I would say, very well documented. There's papers about it. There's tutorials. There's extensive documentation, and so we really hope that the community will start to use it. And then in the last minute, I'll just kind of point out some examples with it. So the first thing that we considered was Higgs to 4 leptons and the vector boson fusion production. We considered these two higher dimensional operators, and we wanted to measure those two EFT coefficients. And so here are the results in that 2-dimensional plane. And this is like a 1-dimensional slice through that plane where you see the log likelihood function. And this, the more narrow this is, the more precise your measurement is. And in that 1-dimensional slice, what you see is that using these new techniques was like adding 90% more LHC data. So that's comparing, for instance, in this case, a 2-dimensional doubly differential cross-section approach, which is already fairly advanced to this fully differential approach. And so you see that you can gain quite a bit in terms of sensitivity. We also did something like this with a much more complicated analysis. It was TTH with the tops going to, the W's going leptonically, and the Higgs to 2 photons. So here you have, missing ET, B jets, lots of jets. You also have reducible backgrounds. And we also included the effect of systematic uncertainties and things like that. And here you see the improvement that you get from, like, say, just using rate information or a singly differential cross-section measurement to using like the fully differential approaches. And then finally was this result that I started with, which shows like in this kind of WH channel, this like very dramatic improvement that you can get compared to simplified template cross sections or even a fully doubly differential approach. And then most recently, there's been some work on looking at diboson production. And so Vulzer and company had first tried to design a good observable. They came up with this angular variable that was useful, but then they've moved to using techniques like what I'm describing, and they have their own slight variation, and they see like significant improvements in that setting as well. So with that, I will conclude and just say that when we're talking about like, real flagship measurements for the LHC, and when we get to them, I think we really want to squeeze out everything that we can. And, if the bottleneck is about reinterpretation, that should be addressed through technical means. We should not, reduce the power of our measurements for what is essentially like a organizational problem. And so the properties we want in our flagship measurements is them, to be, fully differential, to exploit the highest fidelity simulations that we have a very clear and grounded statistical motivation, and to be scalable in terms of how many channels and parameters and things like that. And this approach that I presented in MadMiner, I think, achieves these goals. And with that, thank you very much.
Thank you very much, Kyle. Very good talk. Very a lot of details. So thank you also for sticking to the time. You did a great job. And I want to say, I did mention this earlier, so the speakers of this session can stick around if they choose to, and we will have the discussion session later on. So you can ask a lot of questions then. And I know that Kyle has a few backup slides, and maybe someone is interested in a few more details on the channels or searches he just glossed over now in the last minute. So thanks again, Kyle, and we can come to this in the discussion session if there's interest. Okay.
That's great.
Now
Thank you very much.
Thanks. Now let's move on to our last speaker of this session. His name is Tao Liu from the Hong Kong University of Science and Technology. And also Tao will give us his piece of cake on machine learning. Tao, you can start sharing slides.
Okay, very good.
We can see them, and I can also hear you.
Yes, can you see the screen?
Yes, I can see the screen.
Okay, very good. All right. Before I start, let me thank organizers for inviting me to give this talk. The title for my talk is Unveiling BSM Hidden Physics with Machine Learning. As clearly indicated in the webpage for this workshop, so far, no convincing evidence has been discovered from the LHC analysis. And this situation strongly calls for new ideas, new strategies, which are less model independent and hence allow us to search for highly unexpected signals. And in this regard, machine learning may play a crucial role. For the experimental high energy physics community, actually, there is a long history for model independent searches throughout the lab, Tevatron, LHC epochs. Okay. The basic idea is to compare the data with a simulated background count for each channel over its full or sub phase space. And recently, this class of this idea was correlated to a deep neural network by Andrew Wooser, Simoni, and their collaborators. But here, we hope that we are able to converge the analysis to the region more efficiently where the signal events are rich. This will benefit the sensitivity study and especially the data-driven case and the subsequent new physics identification. In machine learning, there is a class of tasks which are closely related to this goal, namely novelty detection. Novelty detection is a task of classifying test data that differ in some respect from the data that are available during training. That is, there is no priori knowledge available on the signal for such kind of analysis. And if this is a nice review on novelty detection, if we go through this review or read some relevant literatures, then we will say the history of addressing novelty detection is essentially one of developing novelty evaluators or evaluating methods for the testing sample. These evaluating methods in principle can be applied to both semi-supervised learning or fully unsupervised learning, which are distinguished by how to model the backgrounds, either simulation-based or data-driven. Roughly speaking, these novelty evaluators or novelty evaluating methods can be classified into two classes. The first one is isolation-based, and the second one is clustering or density-based. What is isolation-based novelty evaluation? The idea is like this. For a given testing point, its novelty is evaluated according to its distance to the no pattern data distribution in the feature space. And in this plot, the stars represents the testing data, and the magenta points represents the no pattern data distribution. Okay, so for this class of evaluations, the basic idea is to evaluate the novelty response just based on the distance between the given testing point and the no pattern data distribution. Here, the no pattern data distribution could be either from simulation or extrapolation of control region. Okay. So in this process, all of the other testing points in this sample are irrelevant. Okay. So this evaluation is just based on the distance between the testing point and the distribution. Here are a couple of such examples. The first one is related to the method of k-nearest neighbors. The idea is, okay, first, let's calculate the mean distance of the given testing point to its k-nearest neighbors. And then we compare this mean distance with some reference distance which is defined by the training sample. Okay, so here the point is all quantities here are defined with respect to the training sample. Okay, so this is the first example. And in this formula, the train represents the mean distance between the testing point and its k nearest neighbors. And the next one is a reference distance defined by the training sample. And another example is a reconstruction error of autoencoder. For a well-trained autoencoder, the reconstruction error for a given testing point is basically a measure of its distance to the testing points. Okay, sorry. It's basically a measure of the distance of this testing point to the distribution of the known pattern data. Just recall how we calculate the reconstruction error. Okay, such a calculation is just based on individual testing point. And the other testing points in the same sample actually are not directly involved. So in this sense, the reconstruction error of autoencoder is also isolation based. The second class of novelty evaluator is clustering based. Different from the first class of novelty evaluators. In this case, the novelty for a given testing point is evaluated according to the data clustering around this point on top of the no pattern data distribution in the feature space. Okay, again, here the magenta points represent a no pattern data distribution, and the stars represents testing data points. So in this case, the novelty for a given testing point is evaluated based on the clustering around this testing point. Okay. In this case, the testing data around this given testing point, okay, could be relevant. So this is a generic difference between the first class of evaluators and the second class of evaluators. Again, we can take a look at several such examples. The first one is again related to the method of k nearest neighbors. In this case, we can calculate the local densities for the testing data point in both the training sample and the testing sample, just using its k nearest neighbors. Okay, and in this evaluator, here the d-test is mean distance of the testing point to its k nearest neighbors in the testing sample, and the d-train is mean distance of this testing point to its k nearest neighbors in the training sample, and m is a dimension of the feature space. So in this sense, the two quantities in the numerator actually represents the local densities of this testing point in the testing sample and the training sample respectively. So in this case, the novelty response for a given testing point is evaluated by comparing the local densities of this point in the training sample and the testing sample. Okay, this is a method of k nearest neighbors. And another such example is a method proposed by Nachman and Xu, and they named their method as Arnold. Okay, in their paper, they introduce a likelihood. Okay, and this likelihood is defined in equation 3.1. So here, actually, the basic idea is to replace the geometric number density that I just mentioned in previous slide with probability density. Okay, and in this formula, the numerator represents the probability density defined for the testing sample, and the denominator represents the probability density in the training sample. Okay, So basically, this is a comparison of the local density of the testing data point in the training sample and the testing sample. Okay. So by this comparison, we can say these two methods actually share the same spirit. And these two classes of evaluators are developed following different philosophy, okay? They are developed following different lines. One is isolation-based, another one is clustering-based. In principle, these two methods can be combined to achieve a better sensitivity, okay? So here is a simple demonstration. So here is a simple demonstration how to combine these two different types of evaluators. Okay, let's consider a resonance. Let's consider a resonance which is sitting on the tail of the background distribution. And the plot on the right upper corner demonstrates the scores for the testing points based on a clustering-based evaluator. Okay, in this case, here the black curve represents the scores for the known pattern data, and the red curves represent the scores for the unknown pattern data. In this case, you can imagine for the high score points of the, for the high score points in the red bins, some of them are from the signal bin. Okay, this can be understood because of a signal bin, somehow the difference between the local densities in the testing sample and the training sample tend to be relatively big. Okay, and also we can imagine that some of them actually are from fluctuation, are from some region with upper fluctuation, upward fluctuation. Okay, and in this case, the fluctuation, upper fluctuation, can also cause the difference to the local densities of the testing point between the testing sample and the training sample. Okay, so in this case, we say, okay, for the high score testing points can come from either the signal bin and the bin with upward fluctuation. If the high score testing points can be suppressed, and then we would expect a better sensitivity, okay? So this is natural. And indeed, this could be achieved, at least for this simple case. Here the point is that the isolation-based evaluator tend to score high the points from the signal region, because the points from the signal region tend to be far away from the training sample, okay? And for this isolation-based evaluator, they tend to score high the points from the bulk. Okay, so in this case, for example, we can consider geometric mean of these two types of evaluators. Then the high score, okay, then for the testing points from the region with the upward fluctuation, their high score from clustering-based evaluator will be compensated for by the low score from the isolation-based evaluator. Okay. And this slide demonstrates sensitivities based on these different types of evaluators using a toy model. This is a two-dimensional Gaussian model. Okay. So for this toy model, here, the broad distribution represents the no pattern data, and the narrow distribution represents the unknown pattern data. Okay, and their sensitivity curves are provided in the right bottom panel. And in this panel, we can see a black curve that represents the significant performance of fully supervised learning. And the blue curve represents a significant curve from clustering-based novelty detection. As for magenta curve, it represents a sensitivity curve based on isolation-based evaluator. And the combination of the blue curve and the magenta curve, then we get a red curve. Okay, it is based on a combination of the classroom-based evaluator and the isolation-based evaluator. Okay, and from this plot, we can say, indeed, a significant improvement can be achieved by synergize these two different types of evaluators. In addition to these discussions, there exists another important class of algorithms named the weakly supervised learning. And also based on this, somehow the Koala package was developed. Actually, in a quite general context of novelty detection, this algorithm can serve as a booster. Okay, what is that? Okay, let's have some idea about weakly supervised learning first. For weakly supervised learning or Koala, they involve the classification of two mixed samples. Mixed samples means that for both of them, they are composed of signal events and background events, but with different fractions. And in this case, we can still label these two mixed samples as, for example, 0 and 1, and then perform supervised learning to classify these two different samples. And we can mathematically prove that optimizing the classification between these two mixed samples actually is equivalent to optimizing the signal versus background, as long as statistics is big enough. Okay, and if the fraction of signal in the first sample, that is S0 over B0, is equal to 0, and the fraction for the second sample is equal to 1, then this analysis is reduced to fully supervised learning. This is a rough idea about the weakly supervised learning or Koala. Okay. So here the point is, for novelty evaluation that we just discussed, they will generate mixed samples in favor of signal and background respectively. As said, this class of algorithm will help converge our analysis to the region where the signal events are rich, right? To help us to recognize the signal region. Okay, so the novelty evaluation will generate mixed samples in favor of signal and background respectively. And in this case, we can combine the outcomes of novelty evaluation and the weakly supervised learning to further improve the sensitivity performance of the classifier. Okay, so in this sense, we can say somehow the weakly supervised learning can serve as a booster for novelty detection. This is just some general comments. On the data side, last year, Atlas Collaboration submitted their first analysis of digest resonance search using the method of weak supervision. Okay, and using this method, they published the first batch of exclusion limits on the resonance searches based on the topology of PP2A to BC. Okay, so here different bins represent different masses for the particle B and particle C. And for all of them, the mass of the particle A is 3 TeV. Okay. And despite this progress, most of the ideas which have been proposed so far are just a proof of concept. We need to test their performance in a more realistic environment, okay, before they are able to be applied to real data analysis. And largely motivated by this, Nachman and his friends initiate the event, LHC Olympics 2020 Data Challenge. Okay, basically this is just to provide a platform for people to test their ideas or strategies and compare their performance. And more than that, last CERN announced a new open data policy in support of open science. This is great. It provides a great opportunity for people to test their new ideas or new strategies just using the open data. Certainly, this is a more realistic environment, okay? Actually, before this announcement, our colleagues from Caltech already use CMS open data to test their strategy. Okay, and in their paper, somehow they use adversarially land anomaly detection method, and to say whether they are able to rediscover top quark. This method, simply speaking, is a combination of the GAN, generated adversary neural network, and encoder. Okay, so in this paper, they use a CMS open data to say whether they are able to rediscover the top quark. Of course, the answer is yes. Okay, and in the plot at the right bottom corner, it demonstrates the novelty response of the background and signal events from different new physics models. Okay, here is my summary. The null results for new physics searches at LHC strongly call for strategies of searching for highly unexpected signals. And the machine learning techniques developed for novelty or anomaly detection in last decades actually come in handy. And open data committed for open science provides a great opportunity for people to fill up the gap between the proof of concept of these ideas and real data analysis. This is my talk, okay? I will stop here, and thank you for your attention.
Thank you very much, Tao. This was really a great talk and a great segue into the discussion. I'm now calling our discussion leader, Gregor Kaschitska, I hope I pronounced that correctly, from the University of Hamburg. Gregor, the chair and the stage is yours. I want to call all the speakers from this session. If you want to stick around, there might be questions that will be directed at you.
Yes, thank you very much to all three speakers in the session for very interesting talks. I would propose the following way of structuring the discussion now, to go backwards, because of course the talk by Tao is most recently in our memory, so we can immediately direct questions to it. Then have some time to discuss the results presented by Kyle, and then close with Tillman. And once we've done, let's say, one pass of a few questions for each of the contributions, then we can either circle back to maybe topics that are particularly interesting, or discuss larger overarching questions, how machine learning can save particle physics and what particle physics can contribute potentially to research in machine learning. So I think we have several channels via which you can direct questions. You can also anonymously send them to me on Mattermost. And with this, I would like to start and open the floor for questions. First to our most recent speaker, Tao Liu. So I currently don't see raised hands. Ah, there's one raised hand. Yes, Alexander Grosjean, please.
Sorry, Gregor, that was just a mistake on my side. Sorry for that. I changed the view and clicked accidentally on the button. Sorry for that.
Okay. No problem. Okay, I start seeing questions showing up. In the meantime, while people are maybe collecting their thoughts, can you maybe comment on your thoughts on how the interplay of anomaly detection with something like background estimation will be? Because, of course, this cannot, to my understanding, currently be done in a completely model-independent way. So how would you carry out some of these approaches that you discussed in a practical environment?
Okay, for the analysis I demonstrated in this talk, that basically is a semi-supervised study. But as I said, for this class of novelty evaluators or evaluating methods, actually their discussions are separate from how we model the background. So in principle, these evaluators or methods can be applied to both semi-supervised learning and fully unsupervised learning. Okay, this just depends on how we model the background. That is something separate from this this discussion.
Okay, and thinking about structures of anomalies. So do you truly believe, maybe a question of where you think how anomalies look like, but on the one hand, do you think we can do a truly model independent search? And yeah, maybe starting with that.
Truly model independent, how to define truly model independent? Yeah, so here, how to say that? Okay, so if you go to some paper recently written by, I think by Nachman and Xi, somehow they make a broad classification for the collider analysis, the background dependent, background independent, signal dependent, signal independent. So somehow this really depends on how we talk about what I mean, at which level we are talking about model independence. So for this discussions, as said, okay, in terms of the signals, somehow we can safely say, okay, they are model independent. Because here, for the training and for the testing, for the training, and no message, no prior knowledge about signal enters. So in this sense, I think that it is signal independent. Okay. But the question is whether the background is model dependent or model independent. This really depends on how we apply these evaluators. And if we, for example, if we just generate the background by simulation, and for that case, certainly the analysis depends on how we simulate the background. And you can imagine, oh, if there exists some uncertainty from the simulators, then certainly that will cause some anomaly. Okay, so in this sense, somehow, this is background. For the background, it is model dependent. But we can take a further step. We can skip the simulation. We can go to the data directly, right? We can use, for example, the sideband method or ABCD method, then just to model the background by extrapolation of the control region, right? And then for that case, we can say, okay, somehow for the background, it is model independent.
Okay, thank you. I think these set of statements created some reactions. I think maybe we start with the raised hand by Nima.
Yeah, I just had a general comment and question, especially, the name was mentioned in Toman's talk. I might be the only person in this audience who have actually written a paper with Bruce Knudsen a very, very long time ago. Maybe not, but anyway. You collaborated with him. Yeah. Anyway, he was a wonderful, fascinating person, and 15 years ahead of his time, apparently. But let me remind those of you who don't remember Bruce and what he was doing with Vista and Sleuth, what the problem was. And I think his main problem was the look elsewhere effect. His main sort of conceptual problem was when you're just looking for anomalies in zillions of channels. We know that if something goes wrong, it'll go a little wrong in a correlated way in many, many places, and you really suffer to try to figure out how to control the look elsewhere effect. And I think that's basically where he failed. I mean, I remember in applying his technology to like CDF data back then, he found all kinds of spurious sort of 3.5 sigma anomalies in very strange final states with very high multiplicity leptons and B-jets and blah, blah, blah. And there was clearly an issue with not knowing how to sort of control the sort of correlations between many different possible final states. So I think, so I'd like to just ask what sort of, apart from just more computational firepower, there has to be some new conceptual idea to sort of go beyond the sort of bottlenecks that he ran into if we want to, I naively think, maybe you guys have an answer to this question, but I naively think that well, anyway, I'll just ask then, is there a path to go beyond the sort of problem that he ran into?
Okay, regarding the look elsewhere effect, certainly this is a real issue for anomaly detection. And if we go back to my slides, okay, let me share my screen again.
But please try to be concise in the answer because we have 30 minutes to cover all three speakers.
Okay, sure. Okay. Okay. So
I'm actually happy. Sorry, and I'm happy to leave this question for more general discussion as well. If you want to move on to another question right now.
Okay, I will say a little bit about this. Okay, so just I mentioned that for when we evaluate the novelty response, and indeed for some testing points from bug, for example, with upward fluctuations, somehow they will be scored high. In some sense, this is also kind of look elsewhere effect. Okay, so still, for example, by probably combining the different class of evaluators, this effect can be to some extent alleviated. So this is
all I want to say is that this is what Bruce thought about most of all, as far as I remember, and it was still not trivial. But anyway, we can
maybe I can briefly jump in with a comment on this as well, because I think the main conceptual difference is that the classical anomaly detection by Knudsen et al. Is what's currently done in Atlas as general searcher and CMS as music, for example, which relies on a systematic comparison of a simulated background to the recorded data. And there you have the problem that you have many different channels, and you might see too many anomalies because you're looking at essentially too many bins. Several of the anomaly detection methods that were now presented by Tao try to circumvent this by building something that can be trained directly on data to look either for an outlier or for an overdensity in data and not have, let's say, a comparison between many different channels. So I think if you're asking what is the big difference between now and 20 years ago, I think the big difference is that we're now trying to do that more or less completely on data as opposed to comparing data and simulation in some respect.
Okay, thank you.
Kyle, sorry, you had your hand up for a long time.
Yeah, I mean, well, it's all these things are related. I mean, I would just say that with it. So one thing to say is that, these are classical statistics problems that people have thought about for hundreds of years. And we often phrase them in statistics language, and we get really distracted by signals and backgrounds and all of our lingo. In the pure statistical terms, you have a background model and you want to test if it's a goodness of fit test. And one of the problems that, that with goodness of fit tests, which is that they're underspecified. Like there is an infinite family of goodness of fit tests out there that have that reject the background at the right rate. And they all have different power for different possible signals that are out there. So there is provably no good, there's no right answer to this problem. It's totally underspecified. So that's why searches for specific signals, they break that asymmetry by saying, go look here. And so you could, with that in mind, you can take any goodness of fit test and kind of invert it and say it implies that it's sort of powerful for testing some kinds of signals. And if you really want to get to this thing about, there's a trade-off that's fundamental, and you can think of it as how many bins you have. But even if you're doing it in a data-driven way, if you're working with continuous data, it's like an infinite number of bins. So I would not draw that as the fundamental distinction. in the end, you have to, what you need to do, and this is like the bitter pill that physicists are just going to have to swallow at some point, is that you have to, there is no nice answer to this question. So you either just randomly pick something off the shelf and you study its properties, and it is what it is, or you start putting some assumptions in. And the assumptions don't have to come in the form of like a Lagrangian. They can come in the form of smoothness assumptions. Like I think that, you know, random noise is not the signal I'm looking for. The signal I'm looking for is a bump that has a certain length scale associated to it. And so it's all about regularization, and regularization is the key to both taming the look elsewhere effect, because you're not looking for random bumps that are in whatever channels, you're looking for something structured. And the way, and what I think we fundamentally need to do is introduce a new language, a new grammar for describing regularization and smoothness and what kinds of physics, things that we consider to be physical, that are the new signals that are not cast in the form of Lagrangian parameters and things like that. Because if we want to do that, we already have all the machinery to do it. So that's kind of my like rant on that topic.
Thanks. Tillman, yes, do you want to respond immediately to that?
No, just like, you know, my theory take on that is, well, no, I mean, what the Tao and Kyle said is obviously completely right, but I disagree with, sorry, Gregor, I disagree to at some level, you're right, and that nowadays we just try to do this on data, like with anomaly detection, and that works until we don't, until we actually go and like try to understand with the help of Monte Carlo what this anomaly is that we observe, right? And as far as I can tell, I think I agree with Kyle, then the look elsewhere problem is back, right? I mean, it's there, and we have to deal with it, right? I mean, I'm very skeptical of, and this is exactly what Bruce's problem was, right? After I talked with him a lot, right? One of the problems is, okay, you discover something, and it's an anomaly, and okay, like, you know, but we're not interested, like, you know, most anomalies that we see go away because it's some, like, we don't understand something we don't understand, and once we look at it, we understand it, and it's not new physics, right? And now the question is, with these kind of, with these searches, we have an anomaly, we find something, so what do we do next? And Nima, I actually think the Bruce Knudsen problem is still there. And I think it's what Kyle says, and then we have to find a way to do a good analysis and phrase it in a way that, like, you know, the Docker effect doesn't kill us, right?
And I mean, there's a continuum. There's the continuum from like the hyper-specific search to I want to assume nothing. But if you really want to assume nothing, like, you know, it's like there's a worst case scenario. There's like literally the no free lunch theorem, right? You know, like there's not an answer to that question. So like so we need to sit somewhere in the middle, and what we need to do is move the discussion, I feel like, into the field of what are we comfortable with assuming? And is there some new language that we can adopt that's not, you know, the MSSM or something like that?
Just to try to patch in one comment that was made on the Q&A chat, where Darius Farugai says, "Isn't bump hunt a model independent search?" And I don't think it necessarily needs additional answer right now, because I think with what Kyle explained, this ties in already very nicely, because this is exactly the type of physics assumptions we can make to say, okay, we're comfortable with this type of model assumption, and phrasing this as a continuum, I think, is a very nice way. There is maybe one more hand up for Tao before we move on, and this is by Ashutosh. If you would like to ask a question.
Hello, hi, it's Ashutosh Kotwal from Duke. If I could quickly follow up on the comments we just heard from Tillman, Kyle, and Nima. So now it's no problem me saying I am still on CDF. I was on CDF for all the years that Bruce was there, and we were watching very closely with a lot of interest and a lot of encouragement, in fact, to him. But to amplify on what Nima said, there was a slow understanding being gained that as you looked at n final states, each in m bins of histograms, it's n times m, and then the correlations go as the square of that whole thing. So you now start putting numbers like 10 or 20 channels with 10 or 5 bins each. You're down up to 50 square. You're ending up with tens of thousands of correlations. The difficulty within the collaboration was, given that a PP bar collider or a PP collider is a great thing that is broadband, that double-edged sword was coming back to bite us, because broadband collider means that you do not actually have a completely well understood simulation of all those 10,000 or 100,000 elements of the correlation matrix. Nobody will go out there to claim that you actually have a completely inclusive event generator which gets it all, right? As opposed to any plus or minus collider, where you could literally trigger on every collision and simulate every collision in principle, 100 million collisions or 200 million collisions or a billion collisions. In principle, you could make a Monte Carlo sample of 10 billion, which is a replica of your entire inclusive data set. Nobody was going to go out on a limb and say that that's something you could do at a hadron collider. And then to make a claim that those 100,000 correlation matrix elements could be understood was a bit far-fetched. So then people said, okay, that's fine, you give it a best shot. At least it finds anomalies that could then be chased by dedicated analysis. So at least it gave you a pointer in some direction. There were objections to even that philosophically, because if that look elsewhere effect is so large, the probability is very high that 99 or 99.9% of the anomalies are just mismodelings of that in huge correlation matrix. So you will literally just misdirect 100 graduate students chasing 100 fictitious anomalies, and in fact waste the experiment's resource, which is always finite. We could never even publish all the papers that we could with CDF or LHC probably. So if it's in the end a noise finder or a mismodeling finder in a huge, huge parameter space of this correlation matrix, is it really even wise in principle, let alone in practice, but is it even wise in principle to channel the experiment's energies into simply modeling corners and corners and corners of phase space where you don't actually understand if that's a well-motivated corner to chase from a physics angle?
Okay.
So
sorry to cut you off. I think
I'm good. Just a comment.
Tao, do you want to briefly try to answer this? Or other panelists? I think we're in semi-open discussion anyways already. Otherwise, I can briefly answer. So this is exactly what my previous comment was regarding to. The main difference is that this is not now attempt. Well, for me, the main difference, we already observed it with different opinions there. The main difference, as opposed to this approach based on Monte Carlo simulation, is that the new ideas on anomaly detection try to infer as much as possible learning from data, and exactly not try to build something that completely models the simulation. But of course, whenever you leave simulation, you need to make some assumptions about the structure of the signal and the structure of the background to have a tractable anomaly detection problem. Tillman, yes.
Only like loosely related. I mean, also in the Tevatron days, the state of simulations was not comparable to LHC now, right? I mean, if you look at the quality of simulations that we had on the theory side, that we had at Tevatron, I think the people knew pretty well, like where, like, you know, like in which phase space regions and where our theory simulations would just fail. And I mean, in theory simulations, a lot has happened. I mean, this is like, you know, Kyle is like was like referring to this, right? I mean, we have much higher quality and there's much more reliable theory simulations that we can use now. However, I agree with Gregor that for these anomaly searches, well, then you have to think what you want to do. But this is also a different situation to the Tevatron days. I mean, also when people thought it's ridiculous to simulate, like, you know, event samples, like, you know, essentially a Tevatron event sample and look at like event by event compared theory to data, right? I mean, this is not exactly what people do at LHC, but it comes in some analysis pretty close nowadays.
Thanks, Tillman. I would propose, unless there are urgent additional comments on the anomaly detection part, to also give the chance that we actually discuss the content of the other two presentations before we maybe cycle back to that. So I would like to invite specific questions for Kyle and the Mad Miner, or more generally inference-based methods. And since Oliver already spoke of this after your presentation, Kyle, we heard you had some bonus material that you did not show. If I understood that correctly?
I mean, I just, yeah, it was more just like if questions came up. I mean, there's more details about how it works, but I mean, I mean, you know, that's like one of many different pieces of work being done recently on the kind of physics machine learning side of things. So I do think it's interesting. I mean, I guess I could just like say a couple things. One is that you might have noticed that, like, you know, in that talk, there was really no discussion at all about like the architectures of the neural network, right? It was really like the neural network is just kind of like, you know, some function there. And the focus really is actually on the loss functions. And I think that's one of the interesting things is, you know, in machine learning, you know, there's like architectures, and then there's, you know, various kinds of tasks that you want to do. But I think, you know, thinking about like, what is it that I want to do and how do I design a loss function that will achieve that goal is a kind of interesting part of you know, machine learning research. And so there, you know, I think what I like about it partially is that the goal is like, let's cast it in the kind of standard statistical terms and try to figure out a loss function that will allow us to kind of bridge things seamlessly. So the way that I think about that work is really not fundamentally different than the way we do like Higgs to 2 photons with a, or like, you know, the searches with bin template fits and things like that. It's really like you're using a machine learning to try to estimate this distribution, but the formalism is basically unchanged. It's kind of a general point. One other thing that's maybe ties into some of Tillman's stuff is that, you know, so we've written several papers about what I was describing, but sometimes the machine learning is cast, you're trying to learn a likelihood ratio. And in those settings, the problem looks a lot like a classifier. And it looks kind of like what Tao showed with the kind of weakly supervised stuff. There's this so-called likelihood ratio trick that also appears in GANs and various things like that. And but then there's another approach where you just try to directly learn, you know, the distribution itself. And that's kind of these normalizing flow type approaches. So I'm a big fan of normalizing flows. But one thing about those, and you know, essentially all these models, GANs, normalizing flows, et cetera, is that they might do a pretty good job of describing the distribution. But if you can kind of generate some random number and push it through a neural network and get out like an observed one or go the opposite direction, then that model, if it's kind of a deterministic function that goes back and forth, it's never going to really reflect our underlying physical models. It's not going to look like our physical models because our physical models are always these so-called latent variable models. They always have additional sources of randomness inside. And so the structure of the physical generating process has that extra unobserved stuff in it. And so there's this kind of interesting direction, which is, can you come up with neural networks that are structured after the physical generating process, but they're going to involve like additional randomness that you have to integrate out. And so they're going to have some of the similar computational bottlenecks, right? And so, but then there's maybe some, just like we talked about the spectrum between model dependent and model independent, there's also kind of a spectrum between the full-blown GANT, you know, description, and then something like a invertible neural network, which is really like a deterministic function, like, and then something in the middle that has like some essential sources of randomness in it and has some kind of block-like structure to it, you know, so it looks like there's jets over here and electrons over there. And I think that's kind of an interesting direction.
That's a very interesting thought. Thanks. Tillman, you raised your hand.
Yeah, I mean, just because I wasn't very clear about this when I talked about it with Kyle, like what Kyle just mentioned. I mean, it's of course completely right. Normally when you take a normalizing flow, right, you basically map like, you know, a latent space from which you can sample, for instance, to a physics space, and you can actually pad them like with a large number of random numbers on each side, and so then you basically get this, like, you know, the translation in one direction or the other. I didn't actually want to talk about that in detail. This is like in one of my plots that was called the noise extended INNs. So this is one of these like distributions, and the Kyle is completely right. In that they produce some randomness, but very technical speaking, their calibration is relatively horrible. I mean, it might be possible to calibrate them, but it's not at all straightforward. So there is like in this range of neural networks that what Kyle was referring to, like, you know, there is like with this flow networks and the GANs, there's like two steps, right? There's the one where we basically sample, but it's still a deterministic model. And the other one is, I didn't even draw the network, is these conditional setups, where the idea is that you train a model to produce, say, for example, to invert stuff into parton level, to produce parton level events by sampling over random numbers under the condition that you get a detector level event. So as I say, yeah, so Kyle is completely right. So, and then there's the completely random, like, approaches, like, whatever modern stuff you have. So like, from the standard networks to the, like, in the flow networks where you can actually add randomness relatively easily, to the fully conditional approach, then to the proper, like, random generation. I mean, there's a wide range of possibilities. And I agree with Kyle that, well, we know how to do forward, right? And it would be good to, like, get a method to invert it.
I mean, the other thing that's a little bit interesting is that I think in my mind, if you follow this line of logic, you can start to get something where, like, okay, well, let me make like a neural network that's going to be my generative model, but it's going to follow kind of the same broad strokes that you have for like our event generation. Like, you'll have like different steps, and you can kind of learn individual pieces, together, and it can be structured, but it's a big fancy neural network, and you train it, and maybe you can train it on real data. Then you could go to the situation of, well, maybe I can actually discover structure itself, right? So the unfolding is not really like a distribution, it's more like a decay chain or something along those lines. And that's interesting. But, at some point in there, you also get to, well, if I'm going to put all this time into trying to make neural networks that are structured like my physical simulator, like, what's the problem with just using the physical simulator in the first place, right? Like, why not? If you're just, it's already describing those distributions. And so it's a lot of times it's like, well, they have too many constraints in them. So, okay, so the neural networks are maybe describing a more flexible set of things, but, you could certainly, add flexibility to, God forbid, to Pythia and add more parameters or something. But the other big problem is that training them, things like Pythia are not designed for like the way we tune Pythia is ridiculous, right? We generate points, we look at one-dimensional histograms, and we like scan the parameters until the one-dimensional histograms match up. It's ridiculous. If you put on like a machine learning point of view, you would just want to hook up Pythia to the event data and back propagate through it. But there's no technical reason that you can't do that. Like, we should just rewrite our Monte Carlo generators so that they have automatic differentiation capabilities in them. And then you have this other extreme, which is just a differentiable version of like your event generation. Like, that's the extreme version of that. And so it's, there's no neural network involved necessarily. Like, why do I need a ReLU, right? Like, I already know my physics, just use phase space sampling and, and make a much more flexible set of, of splitting functions or whatever, parameterize the hell out of it and differentiate it.
Tilman, one moment. One thought regarding what you just said and also what you said previously. Right now, and I think it was in Tilman's slide, right now, of course, in particle physics, we have a relatively long chain of different tools that historically were built to feed into each other. If you were building such a, let's say, multi-stage latent variable-based approach that has representation at different levels, how closely would you model it according to the architectures we have now, or do you think there is actually a, let's say, better way to structure this problem?
I mean, most of the like core architectural things, like that the parton shower looks like some binary splitting, is like pretty well motivated, I would say. So I mean, I would think it would look pretty similar. I think the other part is, like, if you really examine like how physicists have been successful over millennia in the light of machine learning and AI, like, we have been incredibly data starved, right? We've had really very, very little data and essentially zero compute compared to anything modern. And like, so when I try to figure out like what is the magic, secret sauce that's made this work, part of it is it's more related to these things like causality from the point of view of like statistics and machine learning causality, and like transfer learning and domain adaptation. Like, we know an electron is an electron is an electron, whether it's at an Atlas or CMS or like the Fermi gamma ray, and so we have these like kind of universal components, and we've structured, the problem, and there's a causal there's a causal story. And so like when you learn something that's causal, then you have its, you know, transferability, which makes it incredibly, like, exponentially more data efficient. And like anything that we've talked about, like GANs, flows, all of that, they don't have any causality in them. So like, you know, they're just casting the problem in like purely statistical terms. And what we do as physicists is really like, you know, a broader set of questions that's deeper. And so I feel like, you know, so the nice thing about things like graph neural networks and some of the stuff is that you can start to structure the neural network to mirror the causal story, right? And so that's where I think we should be going. But in the end, the simulators are the causal, they've coded up, you know, at least one version of that causal story. So I think that they're a pretty good start. So like, you know, you can come at it from two different directions. You can make much more flexible simulators and try to add some, you know, some new automatic differentiation capabilities to them, or you can take neural networks and try to make them more, and there's no reason you can't mix and match them, right? You can have Jont with like a little, you know, flow component inside. So I think it will, you know, and then things like learning residuals and stuff will be nice. But, and then when it gets to like Tao's point about anomaly detection, if you have a super structured physical model to describe the data and you basically tune it to the, you know, you fit the observed data, that's your background model, right? And if somewhere in there you see some kind of weird anomaly because you think this thing should be able to transfer to over there, like it's already kind of much more interpretable than it's like, you know, than some, you know, generic black boxy looking thing.
Yeah.
Yes.
Yeah, just, I mean, following like Carl's thought, right? I mean, the first thing I think that's important to like, you know, remember, like, you know, in addition to all the unsupervised stuff, right? Yes, exactly what Carl said, right? I mean, if we stop trying to interpret LHC data in terms of like, you know, our full like, you know, causal, like understood structure and with all the symmetries and everything put in, like, for example, if we start training a pattern shower on data rather than actually trying to explain it in terms of physics, I think we sold out a lot of like, you know, our identity as a field, right? I mean, because I mean, our point is we can understand that stuff theoretically, we can simulate it based on physics, not like based on like modeling. So like, you know, we simulated first principles, we don't model it. Model is easy, modeling is easy. So I totally agree. So like, you know, that structure has to be maintained. When I think about going forward and backward, is like, you know, what Gregor just said. Like, I mean, parts of the simulating chain will benefit from of the simulation will benefit from machine learning, just technically, right? And I think that what's important at this stage now is now that like, you know, Sherpa and MudGraph and all of them are thinking about and like switching to machine learning, like, you know, technology. I think it's important that we think, what can we do in addition, right? I mean, now that we're at it, now that like there will be machine learning MudGraph and a machine learning Sherpa version, like, you know, what can we like, you know, add as requirements and as a conceptual, like, you know, steps forward while we're writing those. And one example, actually, there's, I mean, Kyle, knows this, obviously, there's this paper by Jessica Howard and like, you know, the Irvine group, right? For example, if you think about like simulation, so it's something everybody knows this, but like, you know, they made it explicit, right? If you simulate stuff and then you run it through like Delph, and then you like, you know, essentially produce particles, and then you compare it to something where actually you have run a jet algorithm over stuff. You have somewhere in your simulation chain, you have blown up your number of degrees of freedom enormously, just to like, you know, collapse them at the end of the day to a jet flow momentum that comes out of an algorithm that's designed to reproduce the pattern for momentum which you started from, right? Obviously, when you now want to be fast and efficient in simulating, and since you're rewriting this stuff anyhow, right? I mean, you want like, you know, like links, right? How can I speed up a simulation in case I trust the jet algorithm to a level where, like, you know, I don't want to look inside these things. On the other hand, there will always be problems, subject physics, where you need to look inside, right? So this is like, you know, all the, I think this is why it's crucial that we talk about these things. These, like, you know, what are the opportunities and what are the requirements? What can we do now? Because I expect MudGraph and Sherpa and all of these people to do some significant rewrite of the code with the capabilities that we have, because they need to speed up, as I said, like, you know, right? And we cannot, I mean, we need better and faster simulators.
I think we're very much in open discussion anyways. So if people have additional questions for Tilman, please ask them on any of the channels we opened. Otherwise, we can maybe continue our chat for a bit more. We're also losing participants with the rate of 1 Hertz. So we should come to some conclusion at some point, but I see a raised hand. Alexander, have you switched your screen again?
Right, now it's a serious question, but I don't want to ask Tilman, but Kyle, I have a question on nuisance parameters in the MAD-minor approach. I mean, that was something that you mentioned 2 years ago or 3 years ago in the papers, and now I think you also mentioned nuisance parameters, so systematic uncertainties. Was that something that was recently included? And did you look again at the performance of these algorithms? Because that is, on your third slide or so, right, when you were discussing the different approaches, I mean, this is one of the strengths of this detector level analysis, where you basically include your parameters of interest from the model, so the EFT coefficients, as well as systematic uncertainties, and then you use the data efficiently to constrain systematic uncertainties, right? And that is probably where you gain in this classical approach. Is that something you looked at, or you?
Sorry, I'm muted. I mean, here's just some random slide in the backup that, oh wait, no, it's not displayed in the backup. Skipped. Well, maybe let me unskip it. Well, you can see it there, but I mean, the formalism from the point of view of the machine learning part of it and like the loss functions and et cetera, doesn't make any distinction between the parameters of interest and the nuisance parameters. So you can, what you're doing is you're learning a likelihood ratio function or a likelihood function where you get to plug in data and you get to plug in parameters. And then once you plug those two things in, you evaluate it and you get either a likelihood or a likelihood ratio. And then once you have learned that object, then you can have both parameters of interest and nuisance parameters, and then you can profile them just like we would do with any other kind of statistical model that we built like in the typical way. And so yeah, so MAD-minor supports that, and here was just a result in the MAD-minor paper where we did TT bar Higgs, and you see examples of like with and without uncertainties. And you see even the ellipse even has a slightly different tilt to it and things like that. In terms of where is like improvements of performance come from? I mean, like some of the studies are done where you forget about nuisance systematics and you just look at the difference between being like simplified template cross sections or singly or doubly differential cross sections compared to like fully differential cross sections, and there you can see big improvements just because you're giving it richer data as input. But it's certainly true that once you take into account systematics, you don't want to take an analysis that was designed, neglecting systematics and then and then like propagate uncertainty through it. That will be suboptimal. So here you're learning the likelihood function as a function of both the parameters of interest and the nuisance parameters. And then the profiling is done then at the level of like the final fit, right? So you have all the data, all the different channels, and the constraining power of all the different channels together allows you to eliminate the systematics in kind of like the essentially the optimal way. So it's different than, for instance, like some of the other techniques where we use like this learning to pivot, where we have an adversarial network that tries to learn the best it can under the presence of systematics, but then once you're done, you just have a fixed function. So it's not like that. The stuff we did here, you're like literally learning the dependence explicitly as a function of the nuisance parameters, and then you profile it later. I hope I'm answering your question.
Right. So I just try to match that in my head with the score. I mean, in the score approach, in the end, you just have a multiplication of the score with the actual.
Oh, the score approach. Yeah. In the score approach, you still, so normally they're like the way I defined it. Here's the score. Wait, I'm not sharing my screen, am I? Sorry. here it is. It's the gradient of the log likelihood with respect to the parameter theta. But you can just expand the list theta to include the nuisance parameters as well. And so then the score vector has as many components as, you know, parameters of interest and nuisance parameters. And then this basically carries the necessary information to then assemble the statistical model that depends on both, and then you still profile it later. If you're going to be happy with a kind of elliptical situation, then you can do that, you know, through like geometry. You don't have to like run Minui. You can just, you know, eliminate, if it's an ellipse, you can eliminate the nuisance parameters very straightforwardly.
Okay, thanks.
Sure. I mean, I think I'm happy to talk about it more, you know, offline if it's.
Sure. Yeah, thanks.
Okay, thanks. Slowly winding down, but there was just a question, an additional question on the Q&A from Bogdan Malescu. If you try to quantify the significance of a signal / anomaly, which we could try to convert into a cross-section, the result will depend on the assumptions that are made for the smoothness of the background. In that sense, I think the smoothness assumption do induce a bias. So this is more of a comment than a statement. But
I don't think that, I think that's not the right way to use the term bias. You know, the fact that the result depends on some arbitrary choice is true. We make lots of arbitrary choices, and, you know, our results depend on them. Like, you know, in our analysis, we could use like a, you know, what time is it as my, you know, the test statistic for searching for the Higgs. It's not biased, it's just not sensitive, right? So each choice of the test statistic is going to define a test. The test is going to have type 1 and type 2 error. The power will depend on it, but yeah, I would not call that bias.
Maybe not bias in the statistical sense, but such choices will define to which type of anomaly a specific analysis will be sensitive to.
Yeah, which is the statement of type 1 and type 2 error. Yeah,
sure.
So just cast it in those terms. You know, for this particular signal, I have this power, right? So, and that's where I think, you know, in the anomaly detection discussion, we should really almost always be talking about things like recast also. Because like, say you find some anomaly, you're probably going to want to interpret it in the context of some specific models, right? So like, if you keep that pipeline there, then you can reinterpret it. You can put in a specific test and you can evaluate how sensitive is this random, you know, anomaly detection pipeline to my particular signal. That applies to bump hunts and koala, all those things.
Very much agreed. Good. Looking around on all the different channels, I don't see questions on the Q&A. I don't see questions or raised hands in the chat. I don't see questions posted privately in the Mattermost. I don't see any of the speakers raising their hands. Okay, I think we have exhausted all the energy for questions and discussions we had for today. So thanks again a lot to the organizers and to the speakers of the session and to everybody for this very lively and hopefully, at least it was for me, enlightening discussion. And I think I hand back to Oliver for any closing words from the organizing side.
Thank you, Gregor, and thanks to all the speakers from the session. This was a great discussion. I'm very happy with all the points that were raised. I want to encourage you to follow up on these discussion points and maybe in the Mattermost forum, because this will survive the workshop and we can continue there. And yeah, let me close the workshop for today and invite you to join us tomorrow for the discussion on open data. We'll have many interesting speakers, give us state-of-the-art what's going on at CERN and elsewhere, and it will be interesting. Thank you very much and see you then.
Thank you.
Goodbye.
Take care.
Let's grab a beer together.